How do galaxies interact and merge over cosmic time? What tidal forces create bridges, tails, and new stars during collisions? Why does unseen dark matter play a key role in galactic encounters? When the lights of day fade and the world grows still, our journey begins far beyond the confines of Earth. In the silent depths of space, far beyond the stars we see each night, countless galaxies drift like islands of light in a vast, dark ocean. Each galaxy is a colossal city of stars, hundreds of billions of suns burning across spiraling arms or gathered in smooth, glowing halos. Some galaxies are grand spirals, their starlit arms winding and trailing like delicate cosmic ribbons. Others are enormous elliptical clouds, diffuse and hazy, or irregular clusters of stars in wild, scattered patterns. They gleam softly against the blackness, isolated beacons, separated by unfathomable distances. There are so many galaxies that it challenges the imagination. Astronomers estimate that hundreds of billions, perhaps a trillion or more, populate the observable universe, like lanterns scattered across an endless sea. These galactic islands float alone in the void, each one surrounded by the darkness of intergalactic space. The emptiness between them is so great that if one were to shrink a galaxy down to the size of a glowing disk you could hold, the next nearest galaxy would be many meters away, lost in shadow. For a long time, humanity did not realize that those faint, fuzzy patches in the night sky were not nearby clouds of gas, but entire galaxies unto themselves, far outside the Milky Way. We ourselves live within one of these giant star cities, and for most of history, the others were mere unknown smudges of light. When this truth was finally understood in the last century, the universe suddenly seemed far larger and more mysterious than we had ever imagined. The phrase island universes was coined in an earlier age, and indeed each galaxy is a universe of stars in miniature, containing its own myriad suns, planets, and perhaps life, all bound together by gravity. Imagine drifting gently through this cosmic archipelago. Everywhere around you in the far distance, there are glimmers of light. The soft disk of a spiral galaxy glowing with the combined light of billions of stars. The oval smear of an elliptical galaxy, shining like a distant lantern. The faint spark of a small dwarf galaxy on the periphery. Each one is majestic, yet remote, separated from the next by millions of light years of emptiness. In that immense darkness, galaxies seem solitary and serene, slowly spinning in the quiet of space. Yet they are not entirely alone. Invisible threads of force connect one galaxy to another across the void. Just as gravity binds the stars within a galaxy, it also reaches out beyond each galaxy's edge, tugging ever so gently on its neighbors. Over eons, these distant gravitational tugs begin to weave galaxies into a larger cosmic tapestry, drawing them into groups, clusters, and graceful encounters. In the darkness between the galaxies, an inevitable attraction is at work. One by one, the isolated islands of stars feel the faint pull of others far away. And though it may take billions of years, these forces slowly guide the galaxies into a grand, slow dance through space. Gravity is the great choreographer of this cosmic ballet. Every galaxy, though seemingly isolated, feels the gravitational influence of others. Over millions and billions of years, galaxies move in response to these distant pulls. In small groups of galaxies, 2 or 3 might loop around each other in a slow gravitational dance, as bound to one another as binary stars or planets circling a sun. In massive clusters containing dozens or even hundreds of galaxies, swarms of these star systems orbit a common center of gravity, like a cloud of fireflies drawn into a gentle whirl. The motions are ponderous and stately. A single orbit of one galaxy around another might take 1 billion years or more. Even as the universe itself expands, on these smaller scales, gravity reigns supreme. Within bound groups and clusters, galaxies can draw together, despite the expansion of space. This dance of galaxies is serene but inexorable. Over time, the force of gravity can change the galaxies' destinies. Smaller galaxies often fall under the sway of larger ones, spiraling inward as the eons pass. A great galaxy, like a majestic queen, can capture its diminutive companions, gradually pulling them closer. As a small galaxy drifts too near a larger neighbor, gravitational forces begin to take hold. The stars in the smaller galaxy start to drift away under the influence of the larger galaxy's pull. Its shape can become distorted, stretched into a long stream as stars and gas are drawn off. Eventually, the little galaxy may be completely absorbed, its stars joining the bigger galaxy's halo and disk. In this way, big galaxies grow over time, slowly feasting on those that wander too close, incorporating those stars into their own vast assemblage. Throughout these interactions, the progress is almost imperceptible on human timescales. In a single lifetime, or even over thousands of years, galaxies appear frozen in their grandeur. But if we could watch over the course of many millions of years, we would see the subtle drift. Two galaxies might inch closer together, drawn by mutual gravity. A dwarf companion might slowly arc around a spiral galaxy, each pass bringing it nearer than the last. In the stillness of space, their motion is a stately waltz, slow, graceful, and inevitable. As gravity draws galaxies into these closer steps of the dance, it sets the stage for more dramatic encounters. When two galaxies venture near one another, even before they touch, each feels the other's presence. The delicate balance of their structures begins to shift. Stars that once traveled calmly in circular orbits may start to veer off course, pulled by an unseen influence. The galactic dance, once orderly, becomes more complex and intimate, and with that growing closeness, the first subtle signs of a cosmic encounter begin to appear. When galaxies draw near to one another, they begin to reveal telltale signs of their interaction. What once were orderly, symmetric shapes become distorted. A spiral galaxy that normally has two neat, curved arms might suddenly sport an elongated streamer of stars on one side, reaching out into space. Sometimes two galaxies are seen connected by a faint bridge of light, a tenuous filament of stars and gas linking them across tens of thousands of light years. These are the first whispers of a cosmic encounter. The galaxies' gravities tug at each other, pulling stars and interstellar clouds out of their familiar orbits and into new, delicate patterns. Astronomers have observed many such enchanting distortions. One galaxy might appear to have a flickering tail, a long extension of stars trailing behind it, as if it were dragging a veil of stardust. Another might show a swirling double nucleus, the result of two galactic cores coming together. There are pairs of galaxies that seem to be entwined, spirals wrapped around each other in a gentle embrace. In images from powerful telescopes, we see scenes like a giant pinwheel being tugged at by a smaller companion, its spiral arms stretched toward the companion as though reaching out. In the famous Whirlpool galaxy, for instance, a nearby smaller galaxy pulls on one of its spiral arms, creating a luminous bridge of stars and gas between the two, and causing the whirlpool's pattern to become asymmetrically pronounced. Such sights are snapshots of gravitational interaction in progress, frozen in time for us to behold. Some galaxies even exhibit rings or shells of stars that ripple outward, which can be signs that a smaller galaxy plunged through the heart of a larger one. Like a stone dropped into a cosmic pond, the passing of one galaxy through another can send waves through the larger galaxy's disk. The result may be a striking ring galaxy, a bright ring of stars and gas expanding outward, marking the transient footprint of the intruder's passage. These extraordinary shapes were mysteries when first discovered. Early sky watchers noticed peculiar galaxies that didn't fit the normal spiral or elliptical categories. In time, scientists realized they were witnessing the aftermath of galactic encounters, the graceful yet chaotic disturbances caused when galaxies influence each other. Along with distortions in shape, encounters spark new activity. As galaxies interact, their vast clouds of gas can crash together or be compressed, igniting bursts of star formation in the wake of a close pass or collision. Brilliant blue clusters of newborn stars often light up along the galaxy's arms or in their tidal tails. These young stars burn hot and bright, a telltale sign that the gravitational dance has squeezed gas clouds like a cosmic bellows, breathing new life into them. To observers, an interacting galaxy may shine with unusual brightness in places, glowing with the energy of countless infant suns. It is as if the galaxy's meeting stirs up fireworks on a slow, grand scale, a burst of creation amid the destruction. All these phenomena, the stretched arms, the stellar bridges, the shimmering tidal tails and rings, and the flurries of new stars, are the first signs of cosmic encounters. They are the clues that two galaxies have begun to influence one another's fate. Through these signs, we catch a glimpse of the drama that unfolds when gravity brings galaxies together. Subtle at first, these features herald a transformation that will grow ever more pronounced as the two galaxies draw closer. And behind those elongated tails and ephemeral bridges is the force that creates them, a phenomenon we know from our own seas, now acting on galaxies: tidal forces. The force behind these dramatic distortions is known as tidal force. We experience a mild version of it on Earth. The Moon's gravity pulls a little more strongly on the side of Earth nearest to it, and less on the far side, stretching the oceans into two bulges and giving us the ocean tides. In the vastness of space, the same principle applies on a grand scale. When one galaxy approaches another, the nearer side of each galaxy feels a stronger gravitational pull from its partner than the farther side does. This difference in pull literally stretches each galaxy. Stars and gas on the sides closest to the other galaxy are yanked away from their original orbits. At the same time, the far sides lag behind, held less tightly. The result is that each galaxy can be drawn out into an elongated shape. It is as if the galaxies are pulling taffy, drawing and warping the once orderly spiral or elliptical forms into long, thin extensions. These extensions are the tidal tails and bridges we see. Imagine two galaxies swinging past each other. Each one's gravity snags stars, dust, and gas from the other, flinging this material outward. In some encounters, two such tails stream out in opposite directions, one from each galaxy, tracing graceful arcs through space. A famous example is the antennae Galaxies, a pair of spirals in collision. In their cosmic dance, they have torn two luminous tails of stars from each other, each tail arcing far into the void. Under the telescope's gaze, those twin streaks of starlight resemble the slender antennae of an insect, which is how these galaxies earned their name. Each tail contains billions of stars, cast away into intergalactic space. Some of those stars are likely forever lost to their parent galaxies, set adrift to wander the darkness on their own. Within the tidal tails, gas and dust clump together as they stream out. Remarkably, new stars can be born in these ephemeral strands. Astronomers have even found small embryonic galaxies, called tidal dwarf galaxies, forming out in the tails as concentrated knots of stars and gas collect enough mass to hold themselves together. In this way, a galactic collision can spawn new miniature galaxies, even as the original larger galaxies are being transformed. It's a creative act amid the destruction. Scattered material reassembling in fresh configurations light years away from where it began. Meanwhile, closer to the main bodies of the galaxies, the tidal forces distort their shapes beyond recognition. Spiral arms that once were neatly coiled may be stretched into huge loops or smeared into starry plumes. If one galaxy is much bigger than the other, the smaller one might be completely drawn out, wrapping around the larger like a wispy, starry scarf. If they are more equal in size, both may be heavily warped and tangled, their original forms nearly obliterated in the maelstrom of gravitational forces. Over hundreds of millions of years, these tidal interactions redistribute stars and gas, mixing the contents of the two galaxies. Eventually, as the dance continues, the two galaxies may merge into one, their identities lost in a new blended galaxy, shaped by their mutual gravity. Watching from afar, these long tidal tails and twisted remnants can linger for eons, slowly fading as they disperse. They serve as cosmic footprints, marking where the galaxies have been and how gravity sculpted them. Through these structures, we see gravity's handiwork carved in starlight. But the gravity that molds galaxies during a collision does not come only from the stars we see or the gas that glows. In fact, most of the force drawing galaxies together resides in a form of matter we cannot see at all. Beneath the visible dance of stars and tails lies a hidden influencer, the vast, invisible halos of mass that surround each galaxy. These dark halos are the silent partners in every galactic encounter, and they hold the key to understanding the full story of how galaxies collide. Not all of a galaxy's gravity comes from the stars and gas we can see. In fact, most of it does not. Decades of observations have shown that galaxies are wrapped in halos of invisible matter, far more massive than all their stars combined. Astronomers call this mysterious substance dark matter. It neither emits nor reflects light. We cannot see it glowing in the sky, but its presence is known through its gravitational pull. In the outskirts of galaxies, stars orbit faster than they should if only visible matter existed. Something unseen is holding them in, tugging with a strong gravitational hand. That something is the dark matter halo. Every galaxy is embedded in its own enormous halo of dark matter, extending well beyond the galaxy's visible edges. If one could see a galaxy's halo, it would appear as a vast, dim sphere surrounding the bright spiral or elliptical core, reaching many times the radius of the luminous part. For example, while the Milky Way's visible disk is about 100,000 light-years across, its dark matter halo may span several 100,000 light-years, perhaps more. The Andromeda Galaxy's halo is similarly huge. Recent studies suggest Andromeda's halo stretches out so far that it covers half the distance between Andromeda and the Milky Way. In other words, the halos of our two galaxies might already be touching, overlapping invisibly in the space that separates the galaxies themselves. These hidden halos play a crucial role when galaxies collide. Long before the stars of two approaching galaxies intermingle, their dark matter halos meet and begin to interact gravitationally. Imagine two immense, diffuse clouds of unseen matter colliding gently and merging together. As the halos begin to overlap, their combined gravity increases the pull between the galaxies. Each galaxy feels a stronger drag, as if moving through an invisible, heavy fog. This gravitational drag, a kind of cosmic brake, saps the galaxy's momentum. Over millions of years, it causes the two galaxies to slow their relative motion and draw closer together. Like two dancers moving through a dense mist, the galaxies lose energy to their surroundings and spiral inexorably toward each other. Dark matter halos also help capture smaller galaxies. A passing dwarf galaxy might not even need to venture into the visible disk of a giant galaxy to be captured. The dark halo can snare it first. The dwarf's path can be bent and eventually wrapped into orbit by the halo's extended gravitational field. In time, the dwarf galaxy's own stars and dark matter will disperse into the larger galaxy's halo, adding their mass to it. Through these invisible halos, galaxies can begin merging long before their stars ever touch, and indeed even without direct star collisions at all. It is humbling to realize that the elegant dance of galaxies is choreographed largely by invisible matter. In collisions, stars and gas clouds make for beautiful photographs and vivid fireworks of light. But it is the dark halos that quietly guide the encounter from start to finish. They are the silent architects of the merger, inexorably drawing the galaxies together, absorbing the energy of their motions, and eventually helping them settle into a single new galaxy. Without these massive halos, galaxies might simply swing past one another and separate again. Instead, the halos ensure that once galaxies come sufficiently close, they will likely unite. With this hidden gravity shaping events, we see that galactic collisions are not sudden, violent crashes, but slow, inevitable embraces. Over billions of years, under the influence of both visible and dark matter, two galaxies can coalesce into one. And nowhere is this fate more personally significant to us than in our own cosmic backyard. In the local group of galaxies, our Milky Way is approaching a rendezvous with its neighbour Andromeda, a meeting that will be guided by the massive halos and the gravity we have been contemplating. Now, having set the stage with an understanding of galactic forces and signs, we turn our gaze to this familiar corner of the universe, where a grand cosmic encounter is slowly brewing. We now turn to our own neighbourhood in the cosmos, a small collection of galaxies known as the local group. Here, amid a sprinkling of dozens of tiny dwarf galaxies, two mighty spirals dominate: the Milky Way, our home galaxy, and the Andromeda Galaxy, our great galactic neighbour. These two colossal star systems, each adorned with hundreds of billions of stars, are the principal dancers in our local cosmic ballet. They are currently separated by about 2.5 million light-years, a gulf so vast that even light itself takes millions of years to cross it. Yet in the scale of the universe, this distance is small, and gravity has drawn the Milky Way and Andromeda into a slow but inexorable closing motion. All around them, smaller galaxies orbit like attending companions. The Milky Way is orbited by several dwarf galaxies, and the luminous, large and small Magellanic Clouds, which are slowly being drawn in and disrupted by our galaxy's gravity. Andromeda, too, has a cortege of dwarf galaxies circling it, remnants of earlier acquisitions that have settled into its halo. Our own Milky Way has likely done the same. In fact, astronomers have discovered ghostly streams of stars looping around our galaxy, the telltale debris of smaller galaxies it shredded and absorbed long ago. Our local group is bound together by gravity. The Milky Way, Andromeda, the smaller Triangulum galaxy, and numerous tiny dwarfs are all tied in this gently moving cluster of galaxies, drifting together through space. Within this group, it is the mutual attraction of the Milky Way and Andromeda that dominates the future. At this very moment, the Andromeda galaxy is hurtling toward the Milky Way. Compared to our human experience, this motion is unimaginably slow, on the order of a few hundred kilometers per second across an expanse of emptiness. But with time, it adds up. Each second, the distance between our galaxy and Andromeda shrinks ever so slightly. Across millennia, the change is imperceptible, but across millions of years, Andromeda inches closer. We know of this approach because the light from Andromeda is slightly shifted toward the blue end of the spectrum, a sign that it is moving in our direction. It is one of the few galaxies in the sky that shows this blue shift. Nearly all others are redshifted, receding with the expansion of the universe. Andromeda's blue shift is a cosmic signal that, despite the general expansion of space, gravity is winning here. The Milky Way and Andromeda are bound on a collision course. If you were to look up on a clear, dark night from Earth, you might find Andromeda as a faint smudge of light in the constellation of Andromeda. Through a telescope, it appears as a delicate, elongated blur, the combined glow of all its stars. It is hard to believe that this soft, quiet patch of light is actually an enormous galaxy on a slow collision path with our own. Over the next few billion years, that gentle glow will grow brighter and larger in the sky. Millions of years roll by, and Andromeda draws nearer, until future eyes gazing from the Milky Way would see a huge spiral form dominating the heavens, one that gradually unfurls to fill much of the sky. The two galaxies will begin to disrupt each other long before they fully merge. Andromeda's approaching tide will start to tug on the Milky Way's outer stars, and vice versa. The night skies of Earth, if Earth still exists to witness it, would change dramatically during this time, with a band of foreign stars slowly spreading across the darkness. But all of this lies far in the future. Today, the two galaxies continue their approach in stately silence. It will be on the order of 4 to 5 billion years before the first close encounter truly begins. That timescale is almost impossible to grasp, longer than the Earth has existed as a planet. For now, the cosmic stage is set and the performers are slowly moving into position. Our Milky Way, twirling with its spiral arms full of stars, and Andromeda, sailing steadily toward us across space, are destined to meet. The future collision, a gentle cataclysm spread over billions of years, will reshape them both and create something new. We find ourselves gazing forward in time. The local group, with its two giant galaxies drawing together, stands poised at the threshold of an epical event. In our mind's eye, we can almost see the first faint stirrings of the encounter, the distant halos brushing, the outer stars beginning to feel a new pull. It is a quiet prelude to the grand collision to come. We leave the story here, in a moment of anticipation, with the Milky Way and Andromeda drifting ever closer in the silent darkness. The cosmic dance continues, unhurried and unstoppable, carrying these galaxies toward their destiny. And in time, when the moment is right, those two galaxies will collide and merge, transforming the night sky and giving birth to a new cosmic landscape. That chapter of the story lies ahead, waiting to unfold on the grandest of scales in the eons yet to come. In the darkness between galaxies, two immense star cities drift silently together. They are each 100,000 light-years across, containing hundreds of billions of stars, and they carry with them clouds of gas and dust unseen in the night. As they glide closer, they move at unimaginable speeds, measured in hundreds of kilometers per second. Yet in the vast emptiness of space, their approach feels like a slow, inexorable dance, playing out over eons, quietly guided by the invisible force of gravity. Long before the galaxies truly meet, they sense each other's presence. Each galaxy is enveloped in an unseen halo of dark matter extending far beyond its visible stars, and these ghostly halos begin to overlap and tug on one another, even before any luminous stars draw near. The tenuous outer reaches of each galaxy start to feel that slight gravitational pull as the gravity of one giant island of stars reaches across the void toward the other. Out at the edges, stars and gas clouds are the first to respond, shifting ever so subtly in their orbits. What begins as a gentle nudge will grow into a powerful grasp as the distance between the galaxies shrinks. Gravity accelerates the galaxies toward one another, but it also starts to pull them apart from within. Each galaxy exerts a tidal force on the other, the same kind of force that our moon uses to lift the Earth's oceans in tides. The nearer sides of the galaxies feel a stronger gravitational pull than the far sides, and this difference stretches each galaxy's structure. Like cosmic taffy, their swirling spirals begin to distort and elongate, drawn out of shape by their mutual attraction. The first close pass between the galaxies is not a violent collision of stars, but a gravitational encounter. Despite the sheer number of stars in each galaxy, direct star-on-star collisions are incredibly rare because of the vast distances separating them. The galaxies are mostly empty space on a stellar scale, allowing them to interpenetrate like ghosts passing through one another. But the gravitational interaction is anything but ghostly. It is a forceful exchange of energy and momentum, bending the paths of countless stars and clouds within each galaxy. As they draw within their closest approach, the tidal forces peak in strength. One galaxy might swing past the other, their mutual gravity whipping them around in a dramatic arc. In that moment of near encounter, each galaxy's beautiful spiral arms are flung outward and upward, as if caught in a cosmic whirlwind. Stars that once quietly orbited in a neat disk can find themselves thrown onto new, elongated paths far outside their original homes. Gas clouds are tugged out too, trailing behind like misty streamers. It may seem astonishing, but a cosmic collision of this scale involves almost no direct collisions between individual stars. Consider that each star is like a tiny speck in a vast expanse of space. Even as two galaxies intermix, their stars are akin to two swarms of bees passing through one another. There is a lot of empty space between the bees. The chance of any two stars crashing head-on is extraordinarily low. Instead, the stars simply glide past each other under the influence of gravity, each following a new path dictated by the shifting gravitational landscape. The gravitational dance imparts a kind of cosmic whiplash to the stars and gas at the fringes. Some outer stars gain energy and are flung completely free of their parent galaxy, set adrift to wander into galactic space. Others are captured by the partner galaxy's pull, perhaps destined to join that galaxy instead. Between the two galactic cores, an intricate gravitational tug-of-war unfolds. The result is not chaos in the sense of destruction, but rather a grand reorganization of matter on a colossal scale. During the close pass, the galaxies sway around one another. If their encounter is a near miss, rather than a direct head-on meeting, they may not immediately merge into one. Instead, they swing past and continue on, but not unchanged. Their momentum carries them beyond each other for a time, yet gravity binds them inescapably. Like dancers who twirl apart only to be pulled back by an unbreakable bond, the two galaxies are now gravitationally entwined. They have exchanged energy via the tidal forces, and this energy exchange acts like a brake, slowing their relative motion and ensuring they remain bound. As the galaxies separate after the first pass, they carry with them the imprints of their interaction. Each galaxy is now rippling with disturbances. Waves of motion ripple through their disks from the gravitational shock of the near encounter. The orderly patterns of stars are upset, some moving on radically different trajectories than before. The galaxies themselves are no longer the same pristine spirals they once were, but neither are they wrecked. Rather, they have been profoundly transformed by the passage. Imagine a single star situated at the far edge of one of these approaching galaxies. For eons, that star has calmly orbited the galaxy's center, feeling only the familiar gravity of its own galactic home. As the intruder galaxy draws near, the star experiences a subtle change, an unfamiliar tug from the outside. Over thousands of generations, that gentle pull steadily grows. The star's orbit elongates and is drawn outward. Eventually, the star is no longer bound in its original path at all. It finds itself flung into space, now travelling along with a stream of other displaced stars. What was once a peripheral member of a spiral arm has become part of a tenuous bridge, or tail, connecting two galaxies. This single star, like countless others, has been cast adrift to float in the intergalactic void, forever changed by the brief gravitational encounter. In the aftermath of the close pass, telltale signs of the encounter begin to unfold in space around the galaxies. Stretched arms of starlight extend outward like long, searching fingers. These are the beginnings of features that will evolve into spectacular structures, connecting and trailing the galaxies. They are the direct result of the physics of that near collision. The gravitational forces that acted unevenly across each galaxy have literally reshaped them, pulling stars and gas into new configurations. The physics of a close pass is a ballet of gravity and inertia. The two galaxies, in coming so near, convert some of their orbital energy into internal motions and gravitational potential energy within each other. It is as if the motion that once kept them cruising separately is now being invested in stirring them up. This energy transfer is what creates the grand tidal distortions. As the galaxies arc away from each other after the encounter, we see great luminous arcs and extended halos of matter drawn out in the wake of their meeting. None of this happens in an instant. The closest approach might last tens of millions of years, and the full effect of the pass plays out over hundreds of millions of years. It is slow motion by human standards, but to the galaxies, it is a moment of intense interaction. In the eternity of cosmic time, two galaxies can collide and merge in what seems like a brief, albeit significant, episode. The close pass sets the stage, stirring up the material within them and sowing the seeds of more dramatic changes to come. Gazing at such an event from a great distance, one might not yet see the full spectacle of a merger, but the hints are there. We might observe faint streams of stars and gas beginning to unfurl from the galactic disks. There could be a subtle glow where the two galaxies brushed past each other. illumination from countless stars jostled into new orbits. This is the quiet prelude to the main act of the collision, a tantalizing indication of the transformation underway. From the perspective of any beings that might live inside these galaxies, the encounter would unfold far too slowly to notice in a single lifetime. Night after night, the stars in their sky would appear almost unchanged. Only over many millennia would a pattern emerge, perhaps the faint glow of the other galaxy growing larger, or new stars appearing at the edges of their heavens. The collision is a quiet inevitability, playing out so gradually that it would seem like the cosmos itself is inching forward in time. The two galaxies now have their fates intertwined. No longer free to sail undisturbed, each is captive to the other's gravity. The physics of their close pass has ensured that they will meet again, drawn back for a more intimate encounter. In the meantime, the cosmos has been left with a visible record of their first gravitational embrace. Strewn around them and between them are the early forms of structures born from the encounter, hinting at the grandeur that will fully develop as the collision progresses. In the wake of the galaxy's first close encounter, remarkable structures begin to unfurl. The most striking of these are the tidal tails, immense, elongated streamers of stars and gas that have been pulled out from each galaxy. Picture each galaxy flinging out one or more long arms, stretching far beyond its former boundaries. These tidal tails gleam faintly with the combined light of billions of stars, drawn out into space like a glittering cosmic ribbon. They are like trails of breadcrumbs left behind, marking the path and influence of the encounter. Tidal tails can reach extraordinary lengths, sometimes extending for hundreds of thousands of light years. In fact, they can be larger than the diameters of the original galaxies themselves. Curved by the orbital motion during the encounter, they often sweep out graceful arcs. If one could step back and observe, the pair of interacting galaxies might resemble a celestial creature with long, slender antennae of light, a testament to the powerful gravitational forces that shaped them. Each tail is a mix of old stars that were once part of the galaxy's outer disk, and new stars that may ignite within the tail's gas, triggered into existence by the turmoil. These tails do not remain static. They evolve as the interaction proceeds. Some portions may fall back into the galaxies, while other parts drift off to become isolated stellar streams. For tens or even hundreds of millions of years, the tails remain as luminous reminders of the galaxy's brush with one another. In some instances, the material in a tidal tail can even coalesce under its own gravity to form a small new galaxy, an unexpected offspring of the collision. Eventually, these tails might dissipate into the darkness, or become so faint they blend into the background of space. But for now, they are dramatic signposts of a cosmic encounter. To astronomers, finding such tidal tails is like finding a footprint, evidence that a galactic interaction has taken place. Astronomers have indeed observed such spectacular tidal tails. A famous example is the Antennae Galaxies, a merging pair about 45 million light-years away. They are named for two long, luminous tails of stars and gas unfurling from each galaxy, reminiscent of an insect's antenna. These colossal tidal arms, each extending far beyond the galaxy's cores, formed during the pair's first close pass hundreds of millions of years ago. The antennae's twin tails stand as a vivid real-world confirmation of gravity's ability to reshape galaxies on the grandest scales. One could imagine what it might be like to live on a world situated out in one of those tidal tails. The night sky there would look very different from that in a galaxy's bustling core. the majority of stars would stretch out in a single band or stream across the sky, marking the tail's direction back toward the galaxy's center. In other directions, the sky would be much darker, with only the distant galaxies and the blackness of space. It would be a lonely vista, beautiful and quiet, being on the outskirts of a tidal ribbon suspended between galaxies. Another signature feature of interacting galaxies is the tidal bridge. This is a luminous strand of stars, gas, and dust that forms a direct connection between the two galaxies. In the throes of their close pass, gravitational forces can pull material out from each galaxy toward the other, meeting in the middle as a tenuous link. Imagine two swirling galaxies momentarily connected by a slender, glowing umbilical cord of starlight. For a time, the pair are literally joined by this bridge, sharing matter as well as their gravitational fate. A tidal bridge may be less obvious to spot than a tail, because it stretches between the galaxies themselves, shining against the light of both parent galaxies. Yet it is a remarkable structure, a highway of stars and nebulae drawn from one galaxy to the other. Through this bridge, some stars may actually travel from their original galaxy into its neighbor, swapping homes in the aftermath of the encounter. Gas, too, flows along the bridge, creating a pathway where future star formation could be kindled between the galaxies. Bridges often form when galaxies make a relatively slow, close approach and remain near each other for an extended period. In such a case, their mutual gravitational grip holds some material between them in suspension, rather than flinging it outward entirely. This shared strand of matter underscores just how connected the pair has become. Over time, as the galaxies eventually merge or move apart, the bridge may disperse or fall inwards. But while it lasts, it is a stunning visualization of gravity's reach, appearing almost like a silver thread, sewing the two galactic masses together across space. Tidal bridges have been caught in action as well. The Whirlpool galaxy, for instance, has a smaller companion galaxy, and a faint bridge of light stretches between them. It's a tenuous thread of stars and gas, drawn out by their mutual gravitational tug. Such a bridge could only form from a slow, ongoing interaction, lending credence to our models of how bridges develop during galactic encounters. Not all collisions produce the same kind of debris. While massive spiral galaxies tearing at each other create prominent tails and bridges, there are other, more subtle markers of galactic mergers, especially when one galaxy is much smaller than the other. Among these are the ethereal shells that can appear in a galaxy's outskirts long after a merger has occurred. These shells are faint, arc-like structures, concentric rings or scalloped edges of starlight that wrap around the remnant of a collision. Galactic shells form when a smaller galaxy is accreted by a larger one, particularly in collisions where the smaller companion plunges into a big galaxy's core. As the smaller galaxy's stars are absorbed, they spread out within the larger galaxy's gravitational field. Many of those stars settle into orbits that carry them out to great distances before slowing and turning back inward. At the farthest points of those orbits, the stars tend to cluster, creating a slight overdensity that appears as a brightening, a shell, in the halo of the merged galaxy. These shell structures look like ripples in a pond, frozen in time on a galactic scale. A single merger can produce multiple shells, as waves of stars from the disrupted smaller galaxy pile up at different radii. They are subtle and ghostly, requiring careful observation to detect, but they narrate a story of past cosmic cannibalism. Each shell is essentially a stellar echo of the galaxy that was devoured, a vestige of its stars still coherently moving through the gravitational field of the larger galaxy. Seeing tidal shells is like seeing the faint afterglow of a long-ago feast. They lack the dramatic flair of tidal tales, yet they are profoundly telling. A large elliptical galaxy with faint shell-like rings around it is likely the product of at least one past merger. The shells gradually diffuse and fade over billions of years, but for a significant time, they remain as an archaeological record of the galaxy's violent past, a subtle signature that a collision occurred even if the main wreckage has settled. Astronomers also find the ghostly shells in real galaxies, exactly as the simulations of mergers predict. One striking case is a galaxy designated NGC 474, which is surrounded by multiple faint stellar shells layered around it. These shells appear as curved, concentric arcs, as though ripples spread out from a stone dropped in a pond, but on a galactic scale. Each shell is likely the vestige of a smaller galaxy that was swallowed by NGC 474 in the past. Such observations offer direct evidence of galactic cannibalism, revealing the ancient feasts of giant galaxies. Tails, bridges, and shells represent the visible imprint of gravitational interactions on galaxies. They are the remnants and relics, flung out or arranged in elegant patterns by the tremendous forces at play. Through these structures, the universe itself provides a record of events. Astronomers scanning the skies for these telltale shapes can read the history of galaxies, deciphering which had close encounters, which merged, and which have consumed smaller neighbors. Under the serene appearance of the night sky, these features reveal a cosmos that is dynamic and ever-changing. A galaxy that today shows long tidal tails or delicate shells might have looked very different in the remote past, before the interaction that reshaped it. And as time marches on, those features will evolve further, either dissipating or coalescing into new structures as the collision runs its course. The tails might mix back in, the bridges might fall, and the shells might spread out. But by then, the galaxies themselves will have been forever changed. On the grandest scale, repeated collisions drive the evolution of galaxies over billions of years. In dense clusters of galaxies, where dozens or hundreds of galaxies dwell together, the frequent mergers have produced enormous elliptical giants at the center. These dominant cluster galaxies, sometimes called CD galaxies, are swollen by the accumulated stars of countless devoured neighbors. Often, a diffuse halo of starlight surrounds them, and astronomers detect faint arcs and streams in that halo, the ghosts of galaxies that were torn apart. Such titanic galaxies stand as living evidence that collisions and cannibalism are key mechanisms by which galaxies grow and change over time. All these structural changes are only part of the story. The gravitational dance of the galaxies doesn't just rearrange stars and fling them into space. It also has dramatic effects on the gas within the galaxies. As we move closer to the heart of the collision, we find that the cosmic encounter can ignite brilliant new activity. The next act in this galactic drama will take us from the grand shapes of tidal debris to the glowing nurseries of newborn stars. Stars may have largely sailed past one another unharmed, but the galaxies carry more than stars alone. They are also filled with vast reservoirs of gas, the raw material from which new stars are born. When galaxies crash together, this diffuse gas cannot simply slip by like the stars do. Instead, gas clouds from one galaxy slam into the gas clouds of the other. Enormous shock waves ripple through the interstellar medium. It is as if two giant clouds have collided head-on, compressing and heating the gas between them. In this collision, the calm flow of gas is transformed into turbulent rivers streaming in new directions. Huge tendrils of gas are pulled and stretched, much like the tidal tails of stars. But unlike stars, gas interacts directly. The gravitational forces channel some of the gas along the paths of least resistance, funneling it toward the center of the galaxies. Other gas is forcibly thrown outward into the tidal tails. You can imagine great rivers of glowing hydrogen threading through the merging galaxies, some coursing inward, drawn to the deep gravitational well at the core, and others flowing outward along the elongated arms. These rivers of gas are invisible to the naked eye, but if we could see them, they would appear as immense, swirling currents feeding different regions of the galaxies. Where gas streams converge or pile up, something spectacular happens. The compression of gas triggers the birth of countless new stars. Under normal conditions in a galaxy, star formation might hum along at a steady pace, quietly turning gas into stars at a measured rate. But a galactic collision upsets this balance entirely. When the gas is compressed suddenly and violently, it collapses rapidly into new stars in a burst of frenetic activity. Astronomers call this a starburst, an apt name for what can be a sudden explosion of star birth, as if the galaxy has ignited a brilliant firework display of new suns. Deep in the heart of the interacting galaxies, where their disks overlap and their gravities unite, the star formation is especially intense. As the inner regions of each spiral galaxy crash together, their dense molecular clouds, the nurseries of stars, are squeezed and jostled. In those regions, the rate of star formation can soar to dozens or even hundreds of times the normal rate. Whole clusters of massive stars spring to life in relatively short order. These newborn stars are often colossal in size and extremely hot, emitting a fierce blue-white light. They flood their surroundings with ultraviolet radiation, causing nearby clouds of gas to glow in vivid pink and red hues. Consider one giant cloud of cold molecular gas deep inside one of the galaxies. Before the collision, it has drifted for ages in the galactic disk, slowly churning, but not yet creating any stars. Now, a wave of pressure from the galactic encounter compresses this cloud dramatically. Pockets of gas within it begin to collapse under their own gravity. In a relatively brief span of time, this single cloud fragments into tens of thousands of stars. A brilliant new star cluster is born, where before there was only darkness. The young star's radiation and stellar winds push back against the remaining gas, carving cavities in the cloud. What was once an invisible, quiet gas cloud is now a radiant birthplace of stars, a jewel of light emerging from the turmoil of the collision. The visual spectacle of a starburst region is breathtaking. Imagine sprawling nebulae lit up from within by swarms of hot young stars, much as a city glows at night from its own lights. Enormous glowing clouds of hydrogen, tinged pink by the energetic starlight, billow out in complex shapes. Dark ribbons of dust weave through these glowing regions, silhouetted by the brightness behind them. It is a scene of both creation and chaos. The beauty of new stars being born is entwined with the turbulent forces that forged them. We can witness such cosmic fireworks in action by observing real colliding galaxies. Take the antennae galaxies once more. At their heart, astronomers have found a frenzy of starbirth. The Hubble Space Telescope reveals dozens of young star clusters there, nestled amid chaotic clouds of gas. Rosy nebulae of hydrogen glow intensely under the ultraviolet light of these newborn stars, while dark ribbons of dust thread through the scene. The central regions of the antennae are a tapestry of brilliant blue star clumps and hot pink gas, bearing testimony to a massive burst of star formation set off by the collision. Starburst episodes can make the merging galaxies extraordinarily bright, especially in infrared light. The dust grains mixed in with the gas absorb the intense starlight and re-radiate it as heat, turning the whole central region into a brilliant infrared beacon. Galaxies in the throes of a starburst can outshine entire normal galaxies, becoming some of the most luminous objects in the universe for a time. To observers with the right instruments, they reveal themselves as blazing beacons, announcing that a cosmic merger is driving a frenzy of star-making. Such furious star formation cannot last forever. The galaxies are expending their gas reserves at a breakneck pace. Many of the new stars being born are massive, and massive stars live very short lives by stellar standards, only a few million years. These stars will burn hot and die young, exploding as supernovae. Already, within a few million years of the burst beginning, the first supernova detonations send out blasts of energy and gas, stirring the environment further. The combined effect of many massive stars' stellar winds and supernova explosions can carve out bubbles in the gas and even drive some gas completely out of the galaxy in vast outflows. Over time, these feedback effects, the winds and explosions from the new stars, act to choke off the starburst. They heat and disperse the remaining gas, making it harder for new stars to form. In a matter of tens of millions of years, the starburst will begin to subside as the once plentiful dense gas is either used up or blown away. But while it rages, the starburst dramatically alters the galaxies. It populates them with clusters of young stars and stellar remnants, and it changes the energy balance of the whole system. The remnants of this burst of life will persist, sparkling clusters of stars, some bound together as new globular clusters, and nebula enriched with heavy elements forged in the hearts of the short-lived giants. Astronomers also see the aftermath of such starbursts blowing out of galaxies. One nearby starburst galaxy, known as the Cigar Galaxy, or M82, shows huge plumes of gas streaming outward from its core. This galaxy's intense star formation was triggered by an encounter with a larger neighbor, and now the combined winds of countless supernovae are pushing gas out into intergalactic space. The expelled material glows faintly in red light, tracing enormous bubbles and jets driven by the fury of the starburst. M82's superwind offers a dramatic real-world example of how a burst of starbirth can literally propel matter out of a galaxy. Star formation during collisions isn't confined only to the cores of galaxies. Even out along the tidal tails, in the far-flung reaches of the interacting system, new stars can emerge. The gas that was yanked into a tidal tail may clump together in pockets dense enough to collapse under their own gravity. In those pockets, stars are born far outside the usual confines of a galaxy's disk. Some of these clumps might even become miniature galaxies themselves, so-called tidal dwarf galaxies, assembled from the cast-off debris of the parent galaxies, but shining with the light of new stars. It is a reminder that even in destruction and upheaval, the cosmos finds a way to create anew. Even amid destruction, the cosmos has a way of creating anew. The violence of the collision shatters old patterns, but in doing so, provides the conditions for fresh beginnings. Out of the chaos come new stars, and even new star systems, forged from the compressed gas and dust. In this sense, galactic collisions are an engine of renewal, taking the ingredients of old galaxies and reshuffling them into something different, perhaps even something more vibrant and rich in structure. Amid this burst of creation, the center of each galaxy is undergoing a different kind of awakening. While many gas clouds form stars, some gas is funneled even further inward, toward the very core where a supermassive black hole resides. As the starburst lights up the galaxies, another drama is unfolding in their hearts. The influx of gas toward the core means that not only are stars being fed, but the hunger of a sleeping giant, the central black hole, is about to be sated. With fresh fuel pouring into its vicinity, the black hole is poised to come alive, unleashing energy on a scale that rivals the brilliance of the starburst itself. At the center of each galaxy lies a supermassive black hole, a gravitational behemoth, millions or even billions of times the mass of our Sun. Normally, these dark giants are quiet, lurking in the shadows and steadily holding sway over the stars orbiting the galactic core. But a galactic collision can awaken them. As the galaxies interact, some of the gas that is funneled inward finds its way to the very center, spiraling down toward the waiting black hole. The black hole, which may have been starving for fuel for ages, suddenly has an abundance to feast upon. As gas draws closer to the black hole, it doesn't fall straight in all at once. Instead, it forms a swirling accretion disk around the black hole, orbiting at tremendous speeds. Friction and gravitational forces in this disk heat the gas to extraordinary temperatures, millions of degrees, causing it to blaze with energy. What was once cold, dark, interstellar gas is transformed into a radiant whirlpool of plasma. From the outside, this disk shines brilliantly. We observe it as an intensely luminous core, often outshining the entire galaxy. The once quiescent black hole has become an active galactic nucleus, pouring out light across the spectrum, from X-rays to visible light and beyond. When a black hole feeds, the energy released is prodigious. In some cases, the core of the merging galaxy becomes a quasar, one of the brightest objects in the universe. Quasars appear as ferocious points of light, so luminous that they can be seen billions of light years away. They are powered by the gravitational energy of matter, plunging into the black hole's grasp. For a period of time, the heart of the colliding galaxies may shine like a beacon, outshining even the combined light of billions of stars surrounding it. Such dramatic beacons were far more common in the early universe, when galactic collisions happened more frequently in the crowded young cosmos. Quasars in the distant past numbered in the thousands, lighting up the sky of the early universe as markers of galaxies furiously coming together and growing their black holes. Even in our cosmic neighborhood, many quasars and active galactic nuclei we observe appear to be triggered by interactions or mergers. In rare cases, astronomers have spotted what appear to be double quasars, two blazing galactic cores in the act of merging. These twin lights are likely two supermassive black holes feasting at the same time, a sure sign of a collision in progress and a precursor to their eventual union into one. In today's universe, quasars are comparatively rare, but when we do find one, we often see hints of a collision in its galactic home. Deep observations sometimes reveal that the quasar's host galaxy is not pristine. It may have an irregular shape or faint tidal tails and shells rippling around it. These are the fingerprints of past interactions. Such clues suggest that even now, when we spot a lone quasar shining in the cosmic darkness, there is often an underlying story of two galaxies that merged and ignited that brilliant beacon at the core. This feast is not a gentle one. The infalling gas in the accretion disk can be unstable and chaotic. As it swirls ever faster and hotter, it generates intense radiation pressure. Some of the gas is ultimately swallowed by the black hole, adding to its mass. But a portion of it is also blasted back out by the sheer energy being released. Jets of particles can be launched from the vicinity of the black hole, shooting out along the axis of rotation at nearly the speed of light. These jets pierce through the galaxy, carrying away energy and matter. Meanwhile, powerful winds from the accretion disk blow in every direction, pushing gas outward. The central region becomes a cauldron of high-energy phenomena, a stark contrast to the serene darkness one might expect from the term black hole. Real galaxies provide evidence of these dramatic central awakenings. The nearby galaxy Centaurus A, for instance, is likely the result of an old galactic collision, and it boasts a highly active core. Its central black hole is feeding and blasting out energy. Astronomers observe a colossal jet of particles shooting from Centaurus A's nucleus, extending for tens of thousands of light years. This jet, visible in radio and X-ray light, is powered by the black hole's accretion disk and is a direct manifestation of a galactic core set ablaze. The vivid activity in Centaurus A's heart is a strong hint of the past merger that supplied the fuel, a cosmic beacon heralding that a sleeping giant has awoken. The activation of a galaxy's central black hole can have far-reaching effects on the merger. The energetic radiation and winds from the active nucleus can heat up or expel much of the remaining gas in the core. This feedback can effectively put an end to the furious starburst by depriving it of fuel or heating the gas so it can no longer collapse easily into new stars. In this way, the feeding black hole acts as both creator and destroyer, lighting up the core with brilliance, but also blowing out the materials that could form future generations of stars. The galaxy, in its final merged form, may be left with less gas and a quenched ability to form stars, having been scoured by the quasar-like blaze at its center. In the throes of the merger, there might even be two dueling hearts for a time. Each original galaxy brought its own supermassive black hole to the dance. As the galaxies coalesce, these two black holes are drawn toward each other. Initially, they orbit in the core as a binary pair, circling closer under the influence of dynamical friction with the surrounding stars and gas. Eventually, they may spiral in and merge into one larger black hole. That final union releases an enormous burst of energy in the form of gravitational waves, ripples in the fabric of space-time itself, though these waves would wash over the galaxy and dissipate long before any beings elsewhere could ever detect them. Those gravitational waves rippling outward from a merged pair of supermassive black holes carry away a tiny fraction of the merger's energy. By the time they wash over the wider universe, they are exceedingly weak. Today's gravitational wave observatories are not yet sensitive to such low-frequency waves from galactic-scale mergers, but future instruments might be. Someday, astronomers hope to hear the faint vibrations of space-time from distant galaxy collisions, adding yet another way to study these grand events. When the dust literally settles, the once separate galaxies now form a single entity. At its center sits a supermassive black hole that may have grown significantly from the banquet of infalling gas and the merger of its predecessor black holes. Though the raging quasar phase is temporary, its impact on the galaxy is indelible. The core might remain bright for a time, then gradually calm as the available fuel is consumed or blown away. What remains is a galaxy with a very different character than it had before the collision, one often dominated by older stars, with much of its gas depleted or heated. The lighting of the core is a transformative chapter of the collision's story. In a cosmic blink of an eye, a dark center becomes a beacon, then fades back toward quietude. This drama plays out over perhaps tens of millions to 100 million years. Brief on cosmic timescales, but immensely influential on the galaxy's evolution. The central black hole, once a silent witness to the galaxy's life, becomes an active participant, even a driving force, in the galaxy's rebirth. As the new merged galaxy emerges from chaos, its structure too is settling into place. The violent encounters and gravitational turmoil not only lit up the core and spawned new stars, they have also reconfigured the very shape of the galaxy. The once majestic spiral patterns may be gone, or they may be warped beyond recognition. In their place, new forms are taking shape. Perhaps a ring of stars, a stretched out bar across the core, or a twisted warp in the remaining disk. The cosmic collision has rewritten the galaxy's design, giving rise to features that bear the imprint of the tumultuous events that formed them. When two large spiral galaxies collide head-on and merge completely, the result is often a giant elliptical galaxy. Two majestic disks enter the collision, but one massive ellipsoid of stars emerges, a dramatic transformation. In such a merger, the delicate spiral structures do not survive. Their stars are thrown onto new paths that no longer line up in a flat plane. Astronomers describe this transformation with the term violent relaxation. As the galaxy's gravities yank the stars around, the stellar orbits rapidly randomize into a more chaotic distribution. By the end of the merger, the combined collection of stars settles into a roughly spherical or ellipsoidal shape. The new galaxy has no spiral arms or distinct disk, just a smooth, centrally concentrated glow of old stars. It is a cosmic memory of two former spirals, now blended into one. If we look closely, we might still find faint clues of the past, perhaps those shells or streams in the halo. But to a casual glance, the galaxy is just a massive, featureless ellipse of starlight. The aftermath of a collision can lead to exotic, new galactic forms. One of the most arresting is the ring galaxy, a vast ring of stars and gas that blooms out of the collision like a cosmic ripple on a pond. This can happen when one galaxy plunges directly through the center of another. The force of the passage sends waves of energy outward through the disk of the larger galaxy. In response, the stars and gas are carried outward in an expanding ring. For a time, the galaxy that was once a spiral might have a near-circular ring structure, glowing with intense star formation as the collision's shockwave compresses gas along the ring. Such ring galaxies are rare and short-lived in cosmic terms, but while they exist, they are spectacular. The ring can span hundreds of thousands of light years, often dotted with brilliant blue patches where new stars are forming. It is as if the galaxy wears a diadem of youthful stars along its outer edge. At the center of the ring, one might see the remnant of the original galaxy's core, perhaps a smaller nucleus or a disrupted spiral still trying to reform. The whole scene evokes an image of a bullseye in space, a bright central target encircled by a luminous ring. Over time, the ring will expand and diffuse, and the galaxy may begin to rebuild a more familiar shape. But for that cosmic moment, it bears the unmistakable mark of a head-on collision. Galactic collisions can also sculpt galaxies into new shapes via gravitational resonances and torques. Consider the bar, a straight, elongated band of stars that cuts through the center of many spiral galaxies. Bars can be triggered or enhanced by interactions. When a galaxy experiences the gravitational tug of a passing companion, the orbits of its stars can be perturbed in such a way that they start to sync up into an elongated pattern. Slowly, the spiral galaxy develops a central bar, as if the core has stretched out its arms in opposite directions into a linear form of stars and gas. These bars are not just visual oddities. They play an important role in a galaxy's evolution. The bar acts like a cosmic pipeline, funneling gas from the outer regions toward the center. As the collision or close encounter stirs the galaxy, the bar that forms can drive interstellar matter inward, feeding central starbursts or even the active black hole at the core. The presence of a bar can thus sustain activity in the nucleus long after the initial encounter by continually channeling material inward. Eventually, the bar itself might dissolve or weaken, especially if the galaxy fully merges and becomes an elliptical galaxy without a disk. But in many cases, even after the collision, a merged or disturbed galaxy can retain a disk with a prominent bar, a lasting testament to the gravitational dance that took place. Warps are another consequence of galactic encounters. A warp is a bending of a galaxy's disk, where the outer regions are tilted compared to the inner regions. If a galaxy's disk is like a flat plane of stars, a warp causes the plane to twist into a shallow S-shape or a bowl-like curve. Such deformations can be caused by the tidal forces of an interaction, especially if one galaxy pulls on the outskirts of another at an angle. The stars and gas in the outer disk are shaken from their usual flat orbits and begin to oscillate up and down, creating a corrugated, wavy disk. From afar, a warped galaxy might look like a record or a frisbee that's been gently bent out of shape. One edge of the disk might curl upward, while the opposite edge curls downward. Many spiral galaxies we observe show some degree of warping in their outer regions, suggesting that minor mergers or close passes have disturbed them in the past. Our own Milky Way is no exception. Its outer disk is subtly warped, likely due to interactions with small satellite galaxies, or perhaps the tides from the surrounding cosmic environment. These warps can persist for a long time, slowly flattening out or oscillating as the galaxy settles, but they remain as a lingering memory of an encounter. Not every collision results in a tidy ring or a distinct bar or warp. The outcomes depend on the angles, speeds, and sizes of the galaxies involved. Some collisions, especially between equal-sized galaxies, ultimately destroy the orderly disks altogether, producing a giant elliptical galaxy with little trace of its spiral past. Yet even in those cases, one might find faint shells, as we discussed earlier, or perhaps an inner rotating core, subtle evidence of the tumult that formed it. In other cases, where the collision is more of a glancing blow or involves a much smaller companion, the larger galaxy may survive with its disk intact, albeit embellished with rings, bars, or warps. Each of these structures, rings, bars, and warps, is like a signature of the gravitational interplay that created it. They tell a story written in the shape and motion of stars. A ring galaxy speaks of a dramatic bullseye collision. A barred spiral with an active center hints at past tidal forcing that channeled matter inward. A warped disk whispers of a close encounter that bent its form. To fully decipher these stories, astronomers often turn to another tool: simulations. By recreating these cosmic interactions in computers, scientists speak the language of gravity and motion to unravel how rings, bars, warps, and all the other complex aftermaths of collisions come to be. When two large spiral galaxies collide head-on and merge completely, the result is often a giant elliptical galaxy. Two majestic disks enter the collision, but one massive ellipsoid of stars emerges, a dramatic transformation. In such a merger, the delicate spiral structures do not survive. Their stars are thrown onto new paths that no longer line up in a flat plane. Astronomers describe this transformation with the term violent relaxation. As the galaxy's gravities yank the stars around, the stellar orbits rapidly randomize into a more chaotic distribution. By the end of the merger, the combined collection of stars settles into a roughly spherical or ellipsoidal shape. The new galaxy has no spiral arms or distinct disk, just a smooth, centrally concentrated glow of old stars. It is a cosmic memory of two former spirals, now blended into one. If we look closely, we might still find faint clues of the past, perhaps those shells or streams in the halo. But to a casual glance, the galaxy is just a massive, featureless ellipse of starlight. On the grandest scale, repeated collisions drive the evolution of galaxies over billions of years. In dense clusters of galaxies, frequent mergers have built enormous elliptical galaxies that dominate the cluster cores. The largest of these, sometimes called CD galaxies, sit at the centers of their clusters, enveloped by vast halos of stars. They often carry faint traces of past meals, such as arcs or diffuse light from shredded companions. These giants are living evidence that collisions are a crucial force in growing galaxies. Now, to truly comprehend the complex choreography of colliding galaxies, astronomers have learned to speak in the language of simulations. While telescopes capture single moments of these events, a snapshot of two galaxies in mid-collision, computer models allow us to recreate the entire dance from beginning to end. In a quiet room, a scientist sets up an experiment, not with physical galaxies, but with equations and algorithms. The initial conditions are specified. Two galaxies, each represented by millions of simulated stars and clouds of gas, are placed on a virtual collision course. Then, the clock is set in motion. As the simulation runs, time can be sped up to cover hundreds of millions of years in a matter of seconds. On the screen, the galaxies draw together, interact, and merge, just as real galaxies do over eons. One can watch as spiral arms bend and sway under gravity's pull. Tidal tails unfurl in the model, mirroring those we observe in the cosmos. Bridges of stars stretch between the simulated galaxies, and rings appear when one galaxy punches through another, all confirming that our understanding of the physics can indeed reproduce the phenomena we see in the universe. Early pioneers of this approach used relatively simple simulations to demonstrate the origin of structures like tidal tails and bridges. Decades ago, in the early days of computational astrophysics, astronomers constructed models with only a few hundred particles representing entire galaxies. Even those rudimentary simulations showed that when two galaxies swing past each other, elongated tails naturally form, just as observed in systems like the antennae galaxies. Those early successes were a revelation. They validated the idea that gravity alone, through Newton's laws of motion, could account for the dramatic shapes we see in colliding galaxies. Modern simulations have grown vastly more sophisticated. Today, astronomers use supercomputers to simulate galaxies with millions of particles. These simulations include not just stars, but also gas clouds, and they follow the physics of gas cooling, heating, and star formation. In a state-of-the-art simulation, two spiral galaxies might collide, and the program will create new star particles where gas becomes dense, mimicking the burst of star formation. The simulated galaxies light up with newborn stars and even portray the surge of radiation from active galactic nuclei if enough gas funnels into the center. Essentially, the computer model becomes a miniature universe, obeying the same physical laws, and we get to watch what happens in accelerated time. Over the years, this technique has helped solve cosmic mysteries. For instance, Take a peculiar galaxy with an odd ring of stars or an unexpected double tail. By simulating various collision scenarios, astronomers can determine what kind of interaction produces that specific feature. In one case, it might be a small galaxy plunging through the center of a larger one that creates a stunning ring. In another, perhaps two equal spirals, grazing each other at a certain speed, produce the observed dual tails. The simulation not only reproduces the feature, but provides the narrative, a play-by-play of how that structure came to be, something we could never witness in real time. For example, by simulating the specific case of the antennae galaxies, researchers have been able to recreate their two magnificent tidal tails in detail. By adjusting the masses, approach angle, and timing of two model spirals, the computer generates long stellar plumes, just like those we see in the antennae. Such a close match between a simulation and an actual galaxy is a powerful validation of our understanding. It suggests that the simulated encounter is a true analogue of the real cosmic event that produced the antennae's graceful tails. The language of simulations is mathematics and physics, but its output is visual and intuitive. It translates equations of gravity and fluid dynamics into moving images of galaxies swirling and merging. There is an almost artistic beauty in watching these digital galaxies interact. One can see spiral patterns wind up and vanish, shells of stars ripple out, and cores ignite with concentrated light in the simulation's universe. In a sense, the simulations allow us to see the invisible, to fill in the gaps between the static images we get from telescopes with a continuous, dynamic story. Simulations have also predicted things that were later confirmed by observations. They suggested, for example, that two spiral galaxies merging would likely form a single, rounded, elliptical galaxy. Indeed, many astronomers suspect that large elliptical galaxies are products of past mergers, a view supported by simulations. Simulations have shown how merging galaxies can trigger quasars by funneling gas to the center, a prediction that aligns with observed bursts of quasar activity in interacting systems. They have even been used to preview the far future collision of our own Milky Way with the Andromeda Galaxy. The interplay between simulation and observation is an ongoing dialogue. As new observations reveal unexpected features, perhaps an oddly shaped tidal stream or an unforeseen pattern of star ages in a merger remnant, astronomers go back to their simulations to test if the current models can produce the same results. If not, the physics in the simulation might need refinement or our theories adjusted. Bit by bit, this process improves our understanding of galactic collisions, sharpening the accuracy of the simulations and the insights they provide. Yet, even with powerful computers, there are limits. Simulating an entire galaxy down to every single star is still beyond reach. Approximations must be made. Different simulations might give slightly different outcomes depending on the assumptions. This is why the language of simulations is continuously being refined, incorporating more detailed physics, achieving higher resolution, harnessing faster computing. Each improvement brings the simulated universes closer to reality. Not only can we simulate one collision, but we can also simulate the universe's evolution on a grand scale, to see how common and influential these mergers are. In cosmological simulations, where thousands of galaxies form within a virtual universe, mergers play a leading role in shaping galaxy populations. Spirals grow by consuming smaller dwarfs. Multiple spirals might coalesce into giant ellipticals. The outcome of these large-scale simulations looks very much like the real cosmos we observe, full of diverse galaxies that bear the marks of past mergers. This tells us that without collisions, galaxies as we know them would likely not have evolved into their present forms. Collisions are a central chapter in the cosmic story. In the end, simulations are a tool that lets us experiment with the cosmos in ways we never could directly. They allow us to witness the slow dance of galaxies in compressed time. We can replay those monumental events as often as we like. Simulations also let us probe the underlying causes behind the beauty we see in the sky. Through them, we have gained confidence in our understanding. When galaxies collide, we know broadly how the saga unfolds because we have seen it play out countless times in the virtual realm. From everything we have explored so far, it's clear that every tidal tail, every burst of stars, every lit-up core, and every twisted shape has a story to tell. And through a blend of observation, theory, and simulation, we are learning to read that story. The universe is our teacher, and with each simulated collision, we become more fluent in the language of galactic evolution. The journey of discovery continues, as there are always more cosmic dances to simulate, more celestial tales to decode, and more understanding to be gained about what happens when galaxies collide. In a distant corner of the cosmos, two majestic galaxies drift into each other's embrace. They swirl together in a slow dance, their luminous arms entangling as they begin to merge. Known as the antennae galaxies, this entwined pair glimmers tens of millions of light years from Earth. To the eye, they appear as a tangled haze of stars, with two long arcing streams flung outward, resembling the slender antennae of an insect reaching into space. These graceful tidal tails were drawn out by the gravitational tug-of-war between the galaxies, visible proof of the upheaval that ensues when island universes collide. At the heart of the antennae, chaos and creation go hand in hand. As the two galaxies crash together, immense clouds of gas slam into each other, and shockwaves ripple through them. These shockwaves squeeze the gas like a cosmic vice, triggering a spectacular burst of star formation. Countless new suns ignite in the turbulent overlap where the galaxy's disks intersect. The region is aglow with brilliant young star clusters, some among the most massive ever observed, shining blue-white with the light of hot newborn stars. In only a few tens of millions of years, a blink in cosmic time, billions of stars have been born amid the wreckage. It is a celestial fireworks display, unfolding in extreme slow motion. This cosmic collision has transformed the antennae into a living laboratory of stellar evolution. It offers astronomers a front-row seat to observe how galactic mergers can breathe life into dormant gas. The galaxies were likely ordinary spirals before their encounter, but now they blaze with youthful energy, experiencing a fierce starburst phase. Entangled magnetic fields and turbulent motions, coupled with gravity's relentless pull, have created ideal conditions for rapid starbirth. It is as if two cosmic cities collided, and, in the rubble, new neighborhoods of stars sprang up overnight. The bright knots of light in the antennae tell a story of creation born of destruction. In cosmic terms, the antennae's collision is relatively young. Simulations suggest the two galaxies began interacting about 500 million years ago. And at roughly 60 million light-years from Earth, this pair is one of the nearest major mergers we can observe, offering us a particularly detailed view of such events. Drifting along the long tidal tails are additional clusters of stars, flung far from their original homes. These tails arc into the void, each a stream of stars, gas and dust torn from the parent galaxies. Even out in these extended reaches, star formation has sparked in pockets where gas was compressed in the galaxy's mutual gravitational grip. The tails themselves, so prominent now, are ephemeral structures. Over the next few 100 million years, they will disperse into the surrounding darkness. The stars they contain will either escape as lone wanderers into intergalactic space, or eventually rain back into the merged remnant. For now, however, they stand out as delicate bridges between the galaxies, gossamer strands shimmering with clusters of young blue stars, like beads on a cosmic string. As time flows on, the twin galaxies sink ever deeper into one another. Their separate identities blur as their cores coalesce. The antennae galaxies are on their way to becoming one, perhaps an elliptical galaxy formed from the remnants of two spirals. In the midst of the chaos, the original galactic centers, each once a tranquil hub encircled by spiral arms, are now enveloped in swirling stellar storms. Eventually, these cores will likely unite into a single, larger nucleus. The violence of the merger will give way to a new equilibrium, one combined galaxy born from two. Most likely, it will be a bloated, amorphous galaxy, its youthful star-forming phase fading into a quieter adulthood. What makes the antennae particularly intriguing is how closely it illustrates processes shaping galaxies everywhere. Astronomers see in this collision a preview of what might happen when our Milky Way eventually collides with the Andromeda Galaxy in the far future. In the antennae's glowing arcs and congested core, there is a mirror of our own galaxy's destiny. This relatively nearby merger has been studied intensely, yielding insights into each stage of the cosmic dance. It is no wonder the antennae have been dubbed a cosmic laboratory. They allow scientists to test theories of galactic collisions against the evidence written in starlight and gas. Despite the turmoil, there is a serene beauty to the scene. From afar, one might not sense the enormous forces at work. The two long tails curving outward give the antennae an almost delicate appearance. They sweep into space as graceful extensions of the merging pair, and the main bodies of the galaxies form a luminous, cloud-like shape at their base. The drama unfolds in near silence and extreme slow motion, each galaxy taking hundreds of millions of years to move through the other. Were we able to watch it over eons, we would see the tails gradually unfurl and then dissipate, and the central brightness condense into a single, larger glow. In a human lifetime, the antennae's shape is essentially frozen, caught in one frame of a very long story. Within that still frame, however, myriad changes are occurring. Massive stars born in the starburst live out their short lives in only a few million years, exploding as supernovae that enrich the surrounding gas with heavy elements. These violent stellar deaths add to the turbulence and seed the environment with the ingredients for planets and future generations of stars. Meanwhile, smaller stars begin to settle into clusters. Some clusters may be bound tightly enough to survive the chaos and endure even after the merger, resembling newborn globular clusters. In contrast to the ancient globular clusters that orbit most galaxies, typically relics of the universe's youth, these clusters in the antennae are just a few 100 million years old, mere infants on cosmic scales. They vividly demonstrate that galaxy mergers can rejuvenate galaxies, giving birth to fresh stellar populations, even as they tear apart old structures. Beyond visible light, the antennae tell their tale in other forms of glow. In X-ray light, we see an extended haze of hot gas suffusing the collision zone, a byproduct of the countless supernovae and fast stellar winds heating the space between the stars to tens of millions of degrees. In infrared images, warm dust clouds show up brightly, lit by the new stars hidden within, revealing where embryos of star clusters are still gestating. Radio and millimeter wave observations unveil vast reservoirs of cold molecular gas drawn together by the merger, marked by dense pockets poised to birth the next wave of stars. Each wavelength offers a different perspective on this cosmic upheaval, yet all of them weave together the same story of two galaxies merging and transforming in a blaze of energy and creation. Gently, inexorably, the galaxies continue to merge. The view of the antennae today is a snapshot in the middle of that process, neither the beginning nor the end, but an intermediate chapter. The initial violent pass is behind them, yet the final union lies ahead. The two galactic cores can still be distinguished, but they draw ever closer, linked by streams of stars and gas. Their once orderly spiral arms have been mostly dismantled. What remains is a cloud-like remnant of stars and scattered nebula swirling chaotically. And out of this chaos, as we have seen, come those sweeping tails and radiant star clusters that impose a fleeting order on the scene. The very name antennae captures the imagination. It evokes an image of cosmic insects or celestial butterflies touching delicate feelers in the dark of space. Under the night sky with a telescope, one wouldn't discern this spectacle by eye. The antennae are too distant and faint to be more than a small smudge in amateur instruments. But through powerful observatories, we can trace their shape and glean the physics at play. We see two elongated streams extending from a bright, irregular core. It is a sight both strange and oddly familiar, as if nature repeats patterns at vastly different scales. Just as ocean tides draw long streams of sand and water on a beach, the tides of gravity draw long streams of stars in space. For now, the antennae galaxies remain one of the most striking examples of a cosmic collision caught in the act. They remind us that the night sky's serene beauty conceals ongoing acts of creation and destruction. Here, in this merging galactic pair, cosmic forces are renewing a galaxy's starry population while dismantling its old form. It is a place where one can almost sense the excitement of newborn suns amid the wistful fading of disrupted spiral arms. Through the quiet narration of starlight, the antennae whisper that even in great upheaval, there is balance. The end of one structure becomes the birth of another. High above the merging cores, if one could drift along one of the antenna-like tidal tails, the view would be breathtaking. You would find yourself amid a chain of stars and clusters stretching back toward the distant glow of the colliding galaxies. Out in these tidal streams, the stars are more sparsely scattered than in a galaxy's dense heart, and space feels vast and lonesome. Turning back, you would see the twin galaxies shining as a broken beacon, a double source of soft radiance entwined by filaments of stars. Ahead, the tail thins as it reaches into emptiness, its stars gradually dispersing, some falling behind, others destined to wander on. This stellar stream would be a road to nowhere in particular, a bridge that will eventually dissolve into the night. Yet for now, it is a tangible connection between two galaxies, a glittering reminder of their gravitational dance. The antennae will not remain in this form forever. In a few 100 million more years, the two galactic hearts will likely merge completely. The furious burst of star formation will slow as most of the gas is consumed or blown away by the upheaval. The frantic birth rate of stars will decline to a gentle simmer. What once were two graceful spirals will settle into a single, more rounded mass of stars, Perhaps a faint envelope of gas and dust will surround the new galaxy, debris from the merger enriched by heavy elements forged in the starburst. The resulting system might be an elliptical galaxy, lacking the grand pattern of spiral arms, but full of a mix of stars, young and old. In its halo, some of those young clusters formed during the collision will drift as nascent globular clusters, cosmic souvenirs of the merger. Long after the dramatic merger is complete, subtle traces of the event may linger. Shells or ripple-like patterns of stars could survive as faint structures on the outskirts of the new galaxy, a memory of the time two galaxies became one. Future astronomers, billions of years from now, might study that merged galaxy's odd stellar arrangements and unusual mix of star ages and deduce that it formed from a great collision. In this way, galaxies carry their histories with them, written in the language of starlight and stellar motions. For now, though, the antennae present us with a vivid chapter of galactic evolution in the making. They are a beacon in our cosmic neighborhood, showing us how transformative a galactic collision can be. Peering at the antennae is like watching a fundamental process of creation and destruction play out before our eyes, albeit on a timescale incomprehensibly longer than a human life. The sight inspires a sense of wonder and perspective. It invites us to reflect on our own place in time and space. Our Milky Way, too, will experience a similar merger in the distant future, but on timescales so vast that it hardly troubles our night sky tonight. And yet, through the antennae, we gain a prophetic glimpse of what such a meeting might look like, speeded up in our imagination. From the swirling core where stars are being born by the thousands, to the ethereal tails where stars drift in the aftermath, the antennae encapsulate the grand theme of cosmic evolution, creation out of chaos, unity formed from diversity, change unfolding over unfathomable ages. Watching them, we are reminded that even something as seemingly permanent and majestic as a galaxy is subject to change and renewal. The universe is ever dynamic, and even collisions, which sound violent and catastrophic, can produce scenes of astonishing beauty and new beginnings. Across the cosmos, other galactic encounters produce similarly spectacular tidal tales. These elongated streams of stars are like cosmic signatures, written when galaxies interact and fling out material. The antennae's own tales are beautiful, but there are even more dramatic examples of this celestial art form. In the darkness of deep space, a pair of galaxies nicknamed the Mice chase each other, each dragging a long, slender tail of stars behind it. And in a far-off constellation, a lone spiral called the Tadpole Galaxy stretches a single, enormous tail behind it, as though it were a giant celestial comet. These remarkable systems showcase the art of long tails, ephemeral bridges of starlight that link galaxies fleetingly during their encounters. Far out in the depths of space, the two galaxies known as the Mice exemplify the graceful drama of tidal tales. Each galaxy is a spiral that ventured too close to the other, and now they are caught in a gravitational pas de deux. The nickname Mice comes from their appearance. Each galaxy trails a remarkably long, thin tail of stars, evocative of mice scampering with streaming tails. One galaxy's tail extends in a straight, luminous streak, while the other's fans out in a more curved plume. They seem almost playful in their pose, as if frozen in the act of chasing one another. In reality, these two galaxies have already swung past each other once, and the immense tidal forces of their encounter have drawn out stars and gas into those elegant, filamentary extensions. The formation of such tails is a direct consequence of gravity's uneven pull. When two galaxies approach, The side of each galaxy, nearer its partner, feels a stronger gravitational tug than the far side. This difference, akin to the moon raising tides on Earth's oceans, pulls material outward. In the case of the mice, as the galaxies made their closest pass, each one's stars and clouds of gas were stretched dramatically. The mutual gravity drew out long streamers from their once orderly disks, creating bridges and tails that connect the galaxies across tens of thousands of light years. These tidal streams trace the path of the galaxies' interaction, recording the gravitational dance in trails of starlight. Gazing at the mice through a powerful telescope, one can still discern the individual identities of the two galaxies. They have not yet merged. Instead, they are momentarily entwined, destined to meet and separate and meet again in a slow gravitational waltz. Their cores remain distinct, each glowing as a concentrated knot of light embedded in swirls of disrupted stars. Meanwhile, their tails arch outwards into space. Along those tails are clumps where gas and dust have gathered and even ignited new stars. Each tail is not just a smear of old stars torn from its galaxy, but also a birthplace for a sprinkling of new ones. Tiny blue star clusters dot the tails, hints of fresh life in the aftermath of disruption. These bright specks tell us that even as galaxies are pulled apart, their scattered pieces can light up with new stars. If one were perched on a planet near the tip of one of the mice's tidal tails, the sky would present an awe-inspiring but peculiar vista. Looking along the tail's length, you would see the faint collective glow of countless wayward stars strewn into space, like a tenuous pathway receding into darkness. Far off in one direction, the core of the galaxy you originated from would glimmer as a dense patch of light, the combined radiance of billions of stars from which you have been flung. In the opposite direction, across a gulf of blackness, the companion galaxy would hang in the sky as a hazy, luminous swirl, larger and more magnificent than any object normally seen from a galaxy's outskirts. You might even perceive the companion's own tail, a ghostly streak extending away from its distant core. All around, the rest of the universe would appear nearly empty. To your unaided eye, the tail's stars would be too sparse and faint to form a distinct band. They would meld into the general starry background. Yet their collective motion would carry you inexorably forward, flowing outward along this stellar river. It would be a serene, eerie panorama, a reminder that you are adrift on a narrow bridge of stars cast forth by a galactic encounter. It is striking to consider the fate of these tidal tails. They are transient structures on cosmic timescales. Over the next few 100 million years, the two mice galaxies will likely loop around and collide again, eventually coalescing into one larger system. When that final union happens, their graceful tails will dissipate. Some of the tail stars may fall back and be reabsorbed into the growing merged galaxy's halo. Others might be flung outward permanently, becoming intergalactic drifters. A few especially dense clumps in the tails could remain bound as small satellite star clusters or dwarf galaxies orbiting the merged result. In this way, the mice's encounter will reshape not only the galaxies themselves, but also the space around them, sprinkling stars into the darkness like cosmic confetti. On a grander scale, the image of the mice is a snapshot of a common story in the universe. Many galaxies have likely experienced similar close encounters and sported long tidal tails at one time or another. Often, these events occurred in the distant past, so the telltale streams have long since faded into the stellar halo. In the mice, however, we catch the act unfolding in the present epoch. It offers a window into the mechanics of tidal forces at work. We see clearly how two spiral galaxies, by the simple influence of gravity, can stretch each other into remarkable shapes. Despite the violence implied by ripping stars from their orbits, the scene appears almost gentle. A pair of galactic phantoms gliding past, each trailing a diaphanous veil. The colossal scale and slow pace lend the encounter a ghostly grace. Not far away, in cosmic terms, lies another masterpiece of tidal interaction, the Tadpole Galaxy. This solitary spiral, also known as ARP 188, bears one of the longest known tidal tails. The main body of the tadpole is a distorted spiral galaxy, its once orderly disk disrupted by a past encounter. Where a spiral arm might once have looped symmetrically around, now an extraordinary tail unfurls into space. This tail stretches nearly 300,000 light-years behind the galaxy, a sinuous stream of stars, gas, and dust that fully justifies the galaxy's evocative name. The head of the tadpole is the bright core and remnants of its disk, while the tail trails far off into the cosmic void, dotted with brilliant blue clumps of star formation like beads on a string. The origin of the tadpole's tail is traced to a cosmic near miss. Astronomers believe that a smaller intruder galaxy swept past, or perhaps even briefly through, the Tadpole Galaxy, roughly 100 million years ago. During that close passage, the intruder's gravity drew out the tadpole's stars and gas, pulling them into a tremendous streamer. The small galaxy itself was flung onto a new trajectory. In fact, a faint, compact galaxy is seen just beyond the tip of the tadpole's tail, likely the very culprit that stirred this cosmic disturbance. In effect, the tadpole had its outer layers siphoned off by a passing neighbour. The material wasn't completely stolen away, though. It remains bound by gravity, forming a tenuous rope of stars that still belongs to the tadpole, even as it extends far into space. What makes the tadpole's tail especially stunning is the rich bloom of stars along it. As the gas in the tail condensed in pockets, clusters of new stars ignited. These newborn star clusters gleam with a blue-white light all along the tail's length, creating a sparkling curved bridge leading away from the galaxy. Each cluster may contain hundreds of thousands of stars, some perhaps massive enough to rival globular clusters in brightness, but all very young. It's a vivid illustration of how interactions can trigger star birth even outside a galaxy's main disk, essentially creating miniature galaxies or stellar substructures in the tidal debris. The tadpole's tail is not only a trail of debris, but also a cradle of new stars, making it an incredibly picturesque example of cosmic renewal emerging from chaos. Now imagine standing on a world located within the tadpole galaxy's long tail. The main body of the tadpole, the bright head of the galaxy, would lie far behind you, visible as a hazy, elongated smudge of starlight in one region of the sky. Ahead of you, the tail's stars continue onward, a sparse highway of light diminishing into the great dark beyond. Along that stellar highway, clusters of young blue stars would punctuate the emptiness, each cluster a gleaming oasis born from the tail's gas. Between those clusters, the gaps would be immense and black, the stars thinned out by the stretching of gravity, leaving vast reaches of nothingness. If you looked back along the tail, you might catch sight of a faint blur off to one side, the small intruder galaxy that triggered this spectacular tail, now receding and almost lost against the backdrop of space. The scene around you would be unlike any inside a normal galaxy. An open, lonely expanse with a majestic view of a galaxy far in the distance and a trail of stars leading into the infinite night. It would truly feel like standing on a cosmic bridge, a fragile, transient structure of stars connecting a galaxy to nothingness, destined to disperse but breathtaking while it lasts. In time, the tadpole galaxy's appearance will evolve. Much like a real tadpole in a pond eventually metamorphoses and loses its tail, this galactic tadpole will likely shed its elongated appendage. The tail, being only loosely bound, will disperse over the next few 100 million years. Many of its stars will drift off into intergalactic space. Some may coalesce into one or more diminutive companion galaxies, orbiting what remains of the tadpole. The bright star clusters now strung along the tail could gather into independent star cluster galaxies, essentially the tadpole's offspring. Meanwhile, the tadpole galaxy's core will continue on, perhaps settling back into a less distorted spiral, or merging with another system and becoming an irregular galaxy. Future astronomers, far in the future, might see a relatively normal-looking galaxy accompanied by a few faint satellites, unaware that a vast tail once unfurled from it like a banner. For now, we are fortunate to witness the tadpole galaxy in the throes of its transformation. It stands as a testament to the ephemeral beauty of tidal tails. Alongside the mice, the tadpole shows the variety of forms these tails can take, from twin symmetric streams to a single grand sweep. Both cases underscore a fundamental fact of galactic collisions. Gravity can sculpt galaxies into transient works of art. Tidal tails, lit by swaths of stars, are like cosmic brushstrokes against the dark canvas of space, fleeting and delicate. Eventually, as the moments of their interactions pass, what remains will be changed galaxies, and perhaps only faint remnants of those once glorious tails. Yet even after the tails themselves have dispersed, they leave lasting imprints on their galaxies. The stars scattered by these encounters become part of the galaxy's halos, and the new stellar populations born in the chaos will shine on, long after the tidal structures that birthed them have faded. In this way, each generation of galactic collisions contributes to the evolving tapestry of the universe, adding new stars, redistributing old ones, and subtly reconfiguring the shapes of galaxies. Cosmic modelers have even recreated such tidal tails with computer simulations. By inputting the laws of gravity and setting two model galaxies on a close approach, astronomers can watch virtual galaxies swing by each other and fling out stars and gas, forming spiraling bridges and lengthy streamers. These simulations, pioneered decades ago, demonstrated that tidal forces in a near miss indeed produce features like the mice's twin tails and the tadpole's single plume. The success of such models gives scientists confidence that our understanding of gravity and galactic dynamics explains the stunning shapes we observe. It is remarkable that without any direct collisions between stars, a vast gravitational dance can rearrange whole galaxies into these graceful forms. Not all galactic encounters produce trailing tails. The outcome of a collision depends greatly on the angle and speed of the interacting galaxies. In some cases, when one galaxy plunges directly through the heart of another, a very different structure results, a ring of stars and gas spreading out like ripples on a pond. These collisional ring galaxies are strikingly beautiful and entirely distinct from tidal tails, yet they too are born from gravity's upheaval. A collisional ring galaxy looks like a cosmic ripple frozen in time. Imagine a once normal spiral galaxy struck head-on by a smaller companion moving at high speed. The impact sends a burst of energy coursing outward through the galaxy's disk, like a stone dropped into calm water, creating expanding rings. One of the most famous examples is the Cartwheel Galaxy. From Earth's vantage point, it appears as an almost perfect ring of starlight, with a smaller hub of older stars left at the center. The Cartwheel's outer ring, hundreds of thousands of light years across, glows with clusters of young blue stars, marking where the collision's shockwave compressed gas and triggered furious star formation. Between the bright outer ring and the central hub, faint spoke-like bridges of stars are visible, remnants of the galaxy's original spiral arms, now stretched out by the blast. The outer ring continues to push outward into darkness, a moving front of creation following behind the initial cataclysm. In fact, the Cartwheel also shows a second, smaller ring closer to its core, suggesting that multiple concentric waves rippled through it as a result of the impact. The whole system looks uncannily like its namesake, a wheel with a shining rim and faint spokes radiating inward. In a collisional ring galaxy, the original structure of the galaxy is largely disrupted. The intruding galaxy that caused the ring may have sailed onward, perhaps relatively unscathed, or now a faint companion visible off to the side, while the larger galaxy it pierced is radically transformed. The core of the struck galaxy might survive as a condensed nucleus or inner disk, but around it, the expanding ring carries material far outward. If we could accelerate time, we would see the ring growing in radius and thinning out as it expands. The bright knots of newborn stars in the ring would eventually burn out or disperse. After a few 100 million years, the ring itself may disintegrate, its stars either drawn back inward by gravity or drifting away into space. The end result could be a galaxy with an unusual layered structure, or even a reformed spiral, depending on how the aftermath settles. But for the duration of its existence, the ring is a spectacular, transient feature, a cosmic mandala created by a rare bullseye collision. These ring galaxies illustrate how varied the outcomes of galactic collisions can be. The physics at play is the same, gravity rearranging matter, but the artistry differs with the circumstances of the encounter. A direct, head-on collision produces an outward-moving wave, whereas a glancing blow, as we saw with the mice and tadpole, produces tails. Without seeing examples like the Cartwheel, we might never have guessed that galaxies could wear such a guise. Ring galaxies were once mysterious anomalies. Now we understand them as snapshots of cosmic splash events, graceful in their symmetry, born of violence, yet displaying a kind of order after chaos. For instance, another ring galaxy called ARP 147 presents a vivid cosmic bullseye, a glittering blue ring of stars formed by a collision lying right beside the smaller companion galaxy that pierced through it. In that snapshot, we see the culprit, a disrupted reddish galaxy, still next to the colourful ring it created, a cosmic arrow still lodged in its target. Even more exotic than collisional rings are the so-called polar ring galaxies, true marvels of cosmic geometry. Picture a galaxy similar to our Milky Way, a flattened disk of stars. Now envision a second ring of stars and gas orbiting this galaxy, but oriented perpendicular to the disk, like a halo or a band encircling the galaxy's middle at a right angle. This is the hallmark of a polar ring galaxy, a substantial ring that hovers over the poles of the central galaxy. When viewed from Earth, some polar ring galaxies show a dramatic X shape or cross in the sky. The main galaxy's disk and the perpendicular ring both visible. It's an astonishing configuration, as though the galaxy has donned a gigantic hula hoop, or the rings of Saturn, except on a galactic scale. Polar ring galaxies are exceedingly rare, which makes them all the more intriguing. Only a small number, on the order of 100, are known among the countless galaxies observed. One well-studied example is NGC 4650A, where a sizable ring orbits around a lenticular, lens-shaped galaxy's poles, studded with young blue stars and abundant gas. Another is NGC 660, which presents a striking ring tilted nearly edge-on to our view, looping around its spiral core. These rings are composed of material, stars, gas, and dust that likely did not originate in the central galaxy's disk. Evidence suggests that at some point in the past, a smaller galaxy was torn apart, or a gas-rich dwarf was captured, depositing its contents into a polar orbit around the larger galaxy. Over time, that material coalesced into a stable ring, rotating perpendicular to the main disk. The formation of a polar ring is a quieter affair than the explosive creation of a collisional ring. It might happen gradually. The captured gas slowly settles into its odd orbit and begins forming stars. Unlike the expanding ripple of a head-on collision, a polar ring can persist for a very long time, potentially for billions of years, as a kind of second disk around the galaxy. The dynamics are delicate. The ring must remain stable, and the central galaxy's gravity must provide the right balance to keep the ring intact without absorbing it. Observing these systems provides a unique opportunity to study a galaxy's gravitational field and dark matter halo by seeing how the polar ring orbits. In fact, polar ring galaxies have offered evidence that the dark halo of a galaxy extends far beyond its visible disk. The ring's motion is influenced by unseen mass. They are like cosmic test objects, revealing the presence and shape of dark matter through their unusual kinematics. From a visual perspective, polar ring galaxies are truly marvelous. One can imagine living on a planet within the central galaxy's disk and looking up at the night sky to see a luminous ring of stars arcing overhead at a right angle to the Milky Way-like band of the home galaxy's disk. Conversely, if you were situated within the polar ring itself, you would see the host galaxy's disk stretching across the sky as a spectacular, edge-on band of stars, while your own ring of stars encircled the horizon. These mind-bending perspectives remind us how diverse galaxy structures can be, and how much our viewpoint shapes what we see. Both collisional rings and polar rings serve as reminders that galaxies are dynamic, ever-changing systems. They can be reshaped by interactions in dramatic ways, whether in a single violent burst or through the slow accretion of material. In each case, something unusual and beautiful emerges. A ring where once there was a solid disk, a polar adornment where normally one sees a flat plane of stars. Such features do not last forever, but while they exist, they add to the menagerie of galactic forms found in the universe. The very rarity of polar ring galaxies, for example, makes them precious natural experiments, each one an opportunity to study how a galaxy can acquire and maintain stars in such an offbeat orbit. Yet not all relics of cosmic collisions are so immediately striking. Sometimes the evidence of a galactic merger hides in plain sight, subtle and ghostly. Our own Milky Way, for example, harbours the remnants of past collisions that only reveal themselves as faint streams of stars in the darkness, stellar streams that wind their way around the galaxy, almost invisible except to careful observation. Closer to home, the echoes of ancient galactic collisions surround us in understated ways. The Milky Way, seemingly placid as it arches across our night sky, is in truth a cosmic cannibal. Over its long life, it has consumed numerous smaller galaxies, and the evidence of those feasts lingers as ghostly streams of stars encircling our galactic home. These stellar streams are the remnants of dwarf galaxies and star clusters that ventured too close and were torn apart. They drift through the Milky Way's halo as faint, elongated filaments, the pale, ethereal footprints of devoured companions. One of the most prominent of these streams originates from the Sagittarius dwarf galaxy, a small spheroidal satellite currently in its death throes with the Milky Way. Discovered only in the 1990s, the Sagittarius dwarf was so diffuse and so hidden behind the dense star clouds of the Milky Way's core that it went unnoticed until modern instruments revealed its presence. It orbits our galaxy in a highly inclined polar orbit, passing over the Milky Way's poles, and our galaxy's tidal forces have been steadily pulling it apart. Long strands of the Sagittarius dwarf stars now wrap around the Milky Way like a loose belt. This structure, known as the Sagittarius stream, forms a vast loop, or rather multiple loops, of stars that nearly encircles the sky. Though invisible to the naked eye, it can be mapped by tracking the positions and motions of its constituent stars. It's as if a pale ribbon of starlight has been draped around our galaxy, marking the path of a small galaxy being assimilated. It was astonishing for astronomers to realize that an entire galaxy had been lurking so close to us, hidden in plain sight among the Milky Way's stars, until our surveys became sensitive enough to detect its cohesive motion. Over time, indeed, over billions of years, the remnant of the Sagittarius dwarf will be fully integrated into the Milky Way. Each time the dwarf galaxy swings through the plane of the Milky Way, more of its stars get stripped off, until eventually the dwarf galaxy's core itself will dissolve. The stream it leaves behind is like the fading echo of a galaxy that is being silenced and absorbed. Even now, stars in the Sagittarius stream move in loosely coherent paths, having originated from the same small galaxy. In the far future, they will likely be so dispersed that they blend indistinguishably into the Milky Way's halo population. Future skygazers might notice only a slight overdensity of stars in certain areas, or subtle patterns in stellar velocities to hint that a stream was once there. The Milky Way has other ghosts in its halo as well. The Magellanic Clouds, two dwarf galaxy companions visible in southern skies, are themselves engaged in a gravitational dance with our galaxy. While the large and small Magellanic Clouds remain intact for now, they have left behind an enormous streamer of gas known as the Magellanic Stream. This river of hydrogen gas stretches hundreds of thousands of light years behind them, drawn out by interactions between the clouds and the Milky Way's gravity. Although the Magellanic Stream is composed mostly of gas, hence invisible to optical telescopes, but detectable by radio telescopes, it foreshadows the eventual fate of the Magellanic Clouds. In a few billion years, they too may be stripped of their stars and gas and assimilated into the Milky Way, leaving only tenuous traces like the stream we observe today. All around the Milky Way, astronomers have discovered additional stellar streams, each the remnant of a different accreted satellite. Some streams are relatively large and originate from former dwarf galaxies, not unlike Sagittarius. Others are the shredded remains of globular clusters, ancient dense star clusters that ventured too close to our galaxy's core. One thin stream, for example, has been traced to an old globular cluster being torn apart. Its stars now lie strung out along an orbit, like pearls scattered from a broken necklace. These streams often bear poetic names once identified, labels such as the Orphan Stream or GD1. and each one tells the tale of a cosmic encounter with the Milky Way. They are exceedingly faint and challenging to detect, requiring careful measurements of stars' positions, distances, and motions to tease them out of the vast star field. But as our ability to map the galaxy improves, more and more of these stellar remnants are coming to light, particularly the European Gaia Space Telescope, which precisely measures the positions and velocities of over 1 billion stars, has unveiled many new streams by detecting subtle patterns in stellar motions. With each discovery, the Milky Way's halo appears less like a featureless void and more like a rich tapestry of entwined starry streams, a record of bygone galaxies interwoven with our own. The existence of these streams provides a kind of time-lapse record of the Milky Way's growth. Our galaxy, like all large galaxies, has been built up over billions of years through the merging and accretion of smaller systems. Every time a dwarf galaxy is cannibalized, it contributes not only stars, but also star clusters and dark matter to the Milky Way's halo. In fact, a significant fraction of the Milky Way's outer halo stars are thought to be immigrants, suns that were born in other galaxies and later adopted by the Milky Way. Astronomers have also uncovered evidence for a much earlier and more massive collision in our galaxy's past. Roughly 9 billion years ago, a substantial galaxy appears to have merged into the Milky Way, delivering a huge population of stars to our halo. The stars from that long-ago event have long since dispersed throughout the halo, but they carry telltale chemical fingerprints and distinct orbits that set them apart. By studying these clues, scientists have identified them as the remnants of a vanished galaxy, a ghost of a colossal merger that helped build the Milky Way itself. Despite their tumultuous origins, the stellar streams themselves drift calmly and silently through the dark. If one could travel to a dark, isolated region of the Milky Way's halo, floating among the sparse stars of one of these tidal streams, the scene would hardly resemble the starry vista we know from within the galaxy's disk. Far from the Milky Way's crowded center, the night sky would be almost empty, punctuated by only the faint pinpricks of distant stars. The stream's stars would not stand out as a glowing band to human eyes. They would be too diffuse and dim, indistinguishable from other far-off stars, except for their common motion. The Milky Way itself would appear as a slender, hazy band of light in one part of the sky, a delicate strip of starlight seen from the outside. In these remote reaches, one would truly feel the solitude of space. And yet, one could know that invisibly all around, those stream stars are moving in unison, tracing the ghostly outline of a long-gone companion to our galaxy. They truly are ghosts, visible only when we look with sensitive instruments and discern the subtle patterns they form against the chaos of the halo. These ghost streams around our galaxy are gradually being mixed into the Milky Way, a process that will continue for billions of years to come. And the process is ongoing. The Milky Way still holds dozens of small satellite galaxies in its gravitational grasp, each a potential future stream in formation. In time, unless flung away by some chance, most of those satellites will be stretched out and ingested, adding their stars to our own. The grandest collision on the far horizon for our galaxy, of course, will be with the Andromeda Galaxy, a vast spiral nearly equal in size to the Milky Way. That event, several billion years from now, will utterly reshape both galaxies, perhaps tossing up enormous tidal tails and eventually forming a giant elliptical where two spirals once shone. But even in the present era, on a smaller scale, the slow merging of dwarfs and the resulting streams are quiet preludes to that future spectacle. High above and around us, the Milky Way's halo is a graveyard of past unions and a nursery of sorts for new stars forged by those interactions. Each diffuse arc of stars is a whisper of a meeting long past and a farewell long concluded. In the tranquil darkness of the halo, these streams persist for eons, delicate but enduring threads that enrich and enlarge our galaxy. They remind us that the Milky Way's history is written in the motions of stars, and many of those stars began life in a different galactic abode before finding their final home among the currents of our halo. Modern sky surveys and space telescopes are continuing to unmask these faint structures. With each one identified, we gain another page of our galaxy's autobiography, tales of hunger and growth, of long-lost neighbours whose lights now mingle with our own. While these stellar streams softly tell of past mergers in our galactic neighbourhood, even more dramatic transformations occur in far denser environments. In the crowded cities of galaxies known as clusters, interactions take on a different character. Here, galaxies are not only tugged and tossed by gravity, but are also buffeted by the harsh atmosphere that fills the cluster. Deep in the dense environment of a galaxy cluster, we encounter galaxies undergoing a very different kind of metamorphosis. In these enormous gatherings, hundreds or even thousands of galaxies are bound together by gravity. The space between them is not empty. It is filled with a thin, searing gas at temperatures of tens of millions of degrees, the intracluster medium. As a galaxy plunges through this hot medium, it encounters a pressure like a headwind, even though the air is extremely tenuous. For galaxies falling into the heart of a cluster, this invisible wind can strip away the galaxy's own gas in a violent but largely unseen process. Great clouds of interstellar gas are blown out of the galaxy's disk and trailed behind it. What remains is an eerie sight. A galaxy with bright, streaming tendrils of gas and young stars flowing from its disk, like the tentacles of a jellyfish drifting in the ocean depths. Astronomers call these peculiar objects jellyfish galaxies, and it's easy to see why. In images, one can often make out the galaxy's main body, perhaps a distorted spiral or a once spiral now missing some of its arms. And from one side of it emanate faint, wispy streamers stretching far out into space. These streamers, the tentacles, can reach tens of thousands of light years behind the galaxy. They glow a bluish colour, dotted with clumps of bright young stars that have formed in the gas being swept out. It truly looks as though the galaxy is shedding sparkling pieces of itself as it moves. Each tendril is effectively the galaxy's wake, marking the path it has travelled through the cluster's dense core. The cause of such a dramatic scene is a process known as ram pressure stripping, essentially a cosmic windstorm. As the galaxy speeds through the cluster, often moving at several million kilometers per hour relative to the cluster's center, the pressure of the intracluster medium acts like a gale blowing against the galaxy. The galaxy's own gas, not as tightly bound by gravity as its stars, feels this pressure and begins to give way. It is peeled off layer by layer from the galaxy's leading side and swept downstream into one or more tails. One can visualize a spiral galaxy falling into a cluster. At first, nothing obvious happens beyond perhaps a slight blur of gas forming behind it. Deeper in, a hazy streak develops, the beginnings of a tail. Further in, whole spiral arms worth of gas are streaming backward. Star formation may ignite in those streams, causing bright blue knots to appear like beads on the tail. Eventually, the galaxy's once plentiful supply of cold gas is largely gone, left with only its stars, and perhaps a remnant central gas core. The trailing tail, meanwhile, lengthens and gradually thins out as some of the stripped material disperses into the cluster or lingers in the galaxy's wake like a discarded scarf. For the galaxy itself, this process is transformative. A spiral galaxy rich in gas and actively forming stars can be turned into a gas-poor, quiescent shadow of its former self in a relatively short time, a few 100 million years, which is short compared to a galaxy's life. Deprived of fuel for new stars, the galaxy will gradually age and redden as its existing massive stars die out. Many of the reddish, smooth galaxies that populate the centers of clusters likely followed this path. Once they were star-forming spirals that ventured into the crowded cluster core and were stripped of their gas, their youthful blue sparkle fading into a more somber golden hue. This process contributes to the striking difference we see between galaxies in rich clusters and those in quieter regions. In massive clusters like Coma or Virgo, for instance, the innermost regions are dominated by old, gas-poor galaxies, likely the end products of countless stripping events and mergers over time, whereas out in the field or small groups, spiral galaxies with ample gas are far more common. The harsh cluster environment forces galaxies to grow up quickly, quenching their star formation and altering their appearance. The jellyfish-like tails themselves, though spectacular, are ephemeral. The stars formed in them may remain as small clusters or disperse into the cluster at large, while the stripped gas will eventually mix with the intracluster medium, heating up and becoming part of the general hot plasma background. If we could hover and watch a single jellyfish galaxy over time, we might see its tail gradually fade as the gas becomes diluted, and its star clumps either drift away or fall back toward the galaxy. In some cases, the removed material might even rain down onto the cluster's central region. A portion could be captured by the cluster's dominant galaxy, or even accreted onto that galaxy's central black hole, potentially fueling bursts of energetic activity at the cluster's core. Nothing is truly lost. The gas and stars only relocate, contributing to the cluster in other ways. Astronomers have now identified numerous jellyfish galaxies in various clusters across the universe. With powerful telescopes, we catch these galaxies in the act of being stripped, each one a snapshot of a galaxy mid-transformation, providing insight into how environment can dictate a galaxy's fate. In fact, dedicated searches in recent years have revealed dozens of these galaxies in different clusters, each capturing a galaxy at some particular stage of this stripping process. These discoveries show that ram pressure stripping is a relatively common fate for galaxies that fall into massive clusters, gradually turning blue, star-forming spirals into red, gas-poor cluster members. Looking at a jellyfish galaxy, one can sense both the violence and the poignancy of the process. The violent wind that rips out the galaxy's insides, and the poignant beauty of the sparkling blue diamonds of new stars left trailing behind. There is also something melancholy in seeing a once vibrant spiral being dismantled. Yet, in the grand cosmic balance, the gas one galaxy loses becomes the gain of the cluster. There is a sense of transformation and exchange in this process. The galaxy's loss becomes the cluster's gain. Stripped gas enriches the cluster's reservoir of hot plasma, and stars pulled free of their galaxy may drift into the cluster's common halo, adding a faint, diffuse glow among the other galaxies. The cluster assimilates these offerings, growing ever more massive and luminous, even as individual galaxies are diminished. As dramatic as the jellyfish galaxies are, they are still relatively small happenings on the scale of a galaxy cluster. A single galaxy being stripped is a minor perturbation to the cluster as a whole. The cluster hardly notices, even as the galaxy is profoundly changed. In massive clusters, surrounded by dozens of galaxies and pervaded by hot gas, a jellyfish galaxy is a vivid example of cosmic interplay. It shows that not all galaxy transformations come from direct collisions with another galaxy. Sometimes, the environment itself is the sculptor. The cluster acts almost like a giant organism, influencing and consuming its member galaxies. One galaxy may lose its gas and youthful shine, but the cluster's central regions will glow a bit brighter with the orphaned stars that now wander among the cluster's population, and the intra-cluster medium grows a bit denser with the added gas. After witnessing the fate of individual galaxies in a cluster, one might wonder what happens on an even grander scale. Clusters themselves are not static, isolated entities. They too can collide with one another in events that unleash energies on a truly colossal scale. The next step up in the hierarchy of cosmic collisions involves entire clusters of galaxies running into each other. In these encounters, the scale of the violence and transformation dwarfs even the galactic mergers we have explored, challenging our imagination to grasp such titanic events. When two galaxy clusters collide, we witness one of the most massive events in the universe. These clusters, each a colossal city of galaxies, draped in a cloud of hot gas and embedded in a halo of dark matter, do not meet gently. They rush toward each other over billions of years, drawn together by their mutual gravity, and eventually intermingle in a slow-motion train wreck of truly cosmic proportions. As the clusters begin to overlap, the galaxies within them largely pass by one another without colliding. After all, even within clusters, space is mostly empty. It is exceedingly rare for individual galaxies to directly hit each other during a cluster collision. Instead, the more dramatic interaction occurs between the vast pools of gas that each cluster carries. It is the cluster's gas that truly crashes together. As the cluster cores meet, their great reservoirs of hot gas slam into each other head-on. Enormous shock waves billow out through the merged cluster, heating the gas to even more extreme temperatures and stirring up turbulence that can span millions of light years. One cluster's gas might plow through the others like a snowplow hitting a snowdrift, creating a bow-shaped shock front. Indeed, astronomers have observed exactly this in merging clusters. To human eyes, even those of hypothetical observers living on planets within one of the cluster's galaxies, such a collision would be almost imperceptible. Galaxies would simply grow subtly closer in the sky over countless millennia, and one might notice an increased density of faint smudges, distant galaxies, in one part of the heavens. But there would be no sudden cataclysm visible to the naked eye, nothing as dramatic as the word collision might suggest on human timescales. It all unfolds on scales and over durations far beyond ordinary experience. Yet if we had X-ray vision, the scene would be awe-inspiring. We would see great flashes and surges in the X-ray glow of the intra-cluster gas as the two clusters' atmospheres collide and slow down. One cluster's plasma plows into the others, creating a brilliant arc of X-ray emission, the bow shock, where the gas is compressed and heated to tens of millions of degrees. In the famous bullet cluster, for instance, a smaller subcluster zoomed through a larger cluster, and the hot gas of the smaller cluster was stripped off. It was left trailing behind like a glowing pink cloud, and a clear bow shock marks where it blasted through the bigger cluster's gas. The galaxies, being mostly unhindered by drag, sailed on through, and the bulk of the mass, including the dark matter halo of the bullet subcluster, sped ahead of the colliding gas. In that cosmic bullet's aftermath, we see separated clouds of normal, X-ray bright matter lagging behind, and ghostly concentrations of unseen mass, detected via gravitational lensing, that have moved out in front. This observation offers direct evidence of mysterious dark matter that does not slow down in the collision. The dark matter passed straight through with the galaxies, while the ordinary gas was left behind. Such an extraordinary observation provides some of the best empirical proof that dark matter exists as a separate component of the cosmos. The energy released in a cluster collision like this is almost beyond comprehension. The shock waves can heat gas to hundreds of millions of degrees. Particles accelerated by these shocks emit radio waves, so we often find diffuse radio relics at the periphery of merging clusters. Vast, faint radio glows, marking regions where electrons are spiraling in magnetic fields stirred up by the collision. The total energy output rivals that of the brightest quasars, but spread over an immense volume of space. And yet, because this unfolds in the vacuum of space and across such great distances, it all happens in majestic silence. Over a span of hundreds of millions of years, the two clusters will gradually coalesce into one larger cluster. The shock waves gradually weaken and dissipate, and the hot gas settles into a new equilibrium. The galaxies, now all orbiting within a single deeper gravitational well, carry on their individual journeys, perhaps with slight changes in their orbits from the new gravitational landscape, but largely unaware that they are now part of a merged megacluster. It is a grand cosmic event playing out on a stage of eons. If one could watch in fast forward, one would see the cluster pair slowly coalesce, the gas clouds interpenetrating and then relaxing into a single combined cloud, the galaxies oscillating within the new cluster potential until they settle into new orbits. Even gravitational ripples, gravitational waves, would wash through space from the mass motions, though on a scale far too faint for us to detect. Eventually, the two clusters become one, bigger cluster, and the shock fronts fade away as the system stabilizes. These cluster mergers are the latest step in the hierarchy of cosmic structure formation. Long ago, the universe's matter was gathered into filaments and clumps, and smaller units merged to form larger ones. Galaxies joined into groups, groups into clusters. The collisions of clusters we observe now continue that process of growth. Each time clusters merge, they assemble an even larger cluster, taking one more step toward forming the vast superclusters of galaxies that make up the cosmic web. The newly merged cluster is often chaotic. It may have an irregular shape, with multiple clumps of galaxies and gas still swirling around a common center. Given enough time, even these disturbances will settle, and the cluster will relax into a roughly spherical form. But for a significant period after the collision, the cluster bears the imprints of its violent formation. Much as a galaxy after a merger might show tidal tails or shells, a cluster after a merger might show uneven X-ray structures or an irregular galaxy distribution. X-ray observations, for instance, might reveal lingering shock fronts or asymmetric, plume-like clouds of heated gas in the aftermath, and the galaxies themselves could remain in clumps or streams, not yet fully mixed into a smooth whole. Only after a long interval will gravity iron out these irregularities, but until then, the cluster's appearance carries the scars of its recent trauma. In short, the cluster retains the memory of its collision long after the violence has subsided. Standing back and considering the scale of a cluster collision stretches the imagination to its limits. Picture not just two galaxies colliding, but two entire cities of galaxies, each containing hundreds or thousands of galaxies, passing through one another. The number of stars involved defies counting, yet the distances between those stars are so vast that almost none collide directly. The fundamental forces at play are the same ones that govern more familiar phenomena: gravity, motion, shock waves. But here, they operate on scales that boggle the mind. It's gravity, momentum, and energy exchange, writ enormous across millions of light years. For astronomers, cluster collisions are not only dramatic, they are deeply informative. They provide natural laboratories for understanding dark matter, because, as with the bullet cluster, the separation of normal matter and gravitational mass reveals that much of the cluster's heft is unseen and non-interacting. They also shed light on how galaxies might evolve differently in such extreme environments, since a cluster collision can compress gas and trigger unusual activity in some cluster galaxies by causing them to interact more frequently. There are clusters observed in mid-collision, such as the Pandora's cluster, Abell 2744, where multiple clusters are merging together in a complex, chaotic assembly, the cosmic equivalent of a multi-car pileup on a highway. Each such system provides clues about the sequences of events and the physical conditions during these giant mergers. As we contemplate these titanic collisions, it is almost reassuring to remember that, for all their power, they happen in extreme slow motion. A collision between galaxy clusters may take 1 billion years or more to play out from start to finish. At any given moment, the changes are subtle to any local observer. A galaxy might feel a slight tug. A cloud of gas might brighten very gradually in X-rays. But nothing explodes instantaneously. The timescales of the universe are so vast that even events of tremendous violence unfold gently and gradually from our perspective. It is only by collecting different snapshots, observing various clusters at different stages of merging, and using computer simulations to fill the gaps, that we can narrate the drama in full. And even after a cluster merger is finished, the evolution goes on. The newly formed larger cluster may someday encounter yet another cluster, continuing the cycle of accretion. On the largest scales, structure in the universe grows by the continual merging of smaller units into larger ones. Our own local group of galaxies, relatively small on the cosmic stage, is gradually moving toward the Virgo cluster, the nearest large galaxy cluster, tens of millions of light years away, and may, in billions of years, be captured into that cluster, becoming part of an ever larger assembly. The story of cosmic collisions thus spans all scales, from colliding stars and merging black holes, to galaxies entwining, to clusters crashing together. Each scale brings its own wonders and revelations. We have journeyed through collisions that sculpt galaxies and transform clusters, and yet the cosmic dance is far from over. The forces that draw galaxies together will continue to operate over the eons to come. With each merger and collision, new cosmic structures are born, and the universe around us is reshaped anew. Without a true beginning or end, the grand ballet of creation and destruction carries on, one cosmic encounter at a time, writing the ongoing story of our ever-evolving universe.